What if you could hold a fragment of the universe itself, a piece of history so ancient it existed long before our planet, or even our sun, came to be? These aren't just rocks or dust, they're cosmic relics, time capsules from the very dawn of creation. Think about that for a moment. These artifacts, forged in the fires of dying stars or born in the chaotic aftermath of the Big Bang, carry secrets that could rewrite everything we know about the origins of life, the universe, and our place within it. Today, we're diving into the most incredible artifacts from the dawn of time, stardust older than Earth itself, meteorites that may have carried the building blocks of life, and other celestial treasures that have journeyed across billions of years to reach us. This isn't just a story about space, it's a story about us, about where we came from, and about the mysteries that still lie waiting to be uncovered. So let's step into the cosmos and explore these ancient wonders together. To understand the origins of cosmic relics, we must start at the very beginning, the Big Bang. Nearly 14 billion years ago, the universe burst into existence in an unimaginable explosion of energy. In those first fleeting moments, the cosmos was a seething, chaotic soup of particles, too hot and dense for matter as we know it to form. But as the universe expanded and cooled, the first atoms began to take shape. Hydrogen and helium, the simplest and lightest elements, emerged from the primordial fire. These were the building blocks of everything to come, the seeds of stars, galaxies, and ultimately the very relics we seek to uncover. Yet the story doesn't end there. As the universe continued to evolve, gravity began to pull these clouds of gas together, igniting the first stars. These ancient stars, far more massive and short-lived than our sun, became cosmic forges. Through a process called nucleosynthesis, they fused hydrogen and helium into heavier elements like carbon, oxygen, and iron, elements essential for life as we know it. But these stars didn't last forever. When they reached the end of their lives, they exploded in spectacular supernova, scattering their newly forged elements across the cosmos. These explosions were like cosmic seeders, spreading the raw materials for planets, moons, and even the building blocks of life itself. It's incredible to think that the atoms in your body, the ground beneath your feet, and the air you breathe were once forged in the hearts of these ancient stars. And some of these materials, those that survived billions of years of cosmic chaos, are what we now call cosmic relics. These fragments, whether they're stardust older than our solar system or meteorites that have journeyed across the galaxy, carry with them the fingerprints of the universe's earliest moments. They're not just remnants of the past, they're windows into the very processes that shaped everything we see around us. Imagine holding something in your hand that's older than the Earth, older than the Sun, older than even the solar system itself. That's exactly what stardust is, tiny grains of material that formed in the hearts of ancient stars long before our world existed. These microscopic particles, often no larger than a speck of sand, are cosmic time travelers carrying stories from the universe's infancy. They're not just old, they're ancient, some dating back over 7 billion years. To put that into perspective, these grains were drifting through space before our planet was even a twinkle in the galaxy's eye. So, how do we find something so small and elusive? Stardust is often discovered within meteorites, rocks that have fallen to Earth from space. These meteorites act like cosmic treasure chests, preserving stardust grains that have survived the chaos of supernova, the formation of planets, and the harsh journey through space. Scientists use advanced techniques like isotopic analysis to study these grains. By examining the unique chemical signatures within the stardust, they can determine not only its age but also the specific stars it came from. It's like reading a cosmic fingerprint, one that tells us exactly where and when these particles were born. One of the most astonishing discoveries came in recent years when researchers identified stardust grains that were over 7 billion years old. These ancient particles found in a meteorite that landed in Australia are the oldest solid material ever discovered on Earth. They offer a direct glimpse into the universe's earliest days, a time when the first stars were lighting up the cosmos. But the story doesn't stop there. These grains also reveal the conditions inside those ancient stars, showing us how they lived, burned, and ultimately died, scattering their remnants across the galaxy. What makes Stardust so special isn't just its age. It's the connection it creates between us and the cosmos. Every atom in your body, every piece of the world around you was once part of a star. Stardust is the tangible proof of that connection, a reminder that we are, quite literally, made of the same stuff as the universe itself. It's not just a scientific curiosity, it's a bridge to our origins, a way to touch the very beginnings of everything. And as we continue to study these ancient grains, we're not just uncovering the past, we're piecing together the story of how we came to be. While Stardust offers us a glimpse into the universe's earliest days, meteorites bring us closer to home, carrying secrets from the birth of our own solar system. These rocky visitors from space are more than just random debris. They're time capsules preserving the raw materials and conditions that existed over 4.5 billion years ago, when the sun and planets were just beginning to form. Imagine holding a piece of the solar system's infancy, a fragment of history that predates even the oldest rocks on Earth. That's exactly what meteorites give us, a direct connection to the cosmic processes that shaped our corner of the universe. Meteorites come in a variety of types, each telling its own unique story. Chondrites, for example, are among the most primitive, containing tiny spherical structures called chondrules that formed in the early solar nebula. These stones are like snapshots frozen in time, capturing the moment when dust and gas began to clump together, eventually giving rise to planets. Then there are iron meteorites, which are thought to come from the cores of ancient asteroids. These dense metallic rocks offer a glimpse into the violent collisions and melting that occurred as asteroids formed and broke apart. Each type of meteorite is a puzzle piece, helping us reconstruct the chaotic early days of our solar system. One of the most famous meteorites, the Allende meteorite, is a treasure trove of cosmic history. When it fell in Mexico in 1969, scientists quickly realized it was no ordinary rock. Inside, they found pre-solar grains, stardust older than the sun itself, as well as organic compounds like amino acids, the building blocks of life. These discoveries didn't just deepen our understanding of the solar system's formation, they also raised tantalizing questions about how life might have begun. Could meteorites have delivered the ingredients for life to Earth? It's a possibility that continues to captivate researchers. But meteorites don't just tell us about the past, they also help us understand the present. By studying their composition, scientists can piece together how planets and asteroids formed, differentiated, and evolved. For example, the presence of certain minerals in meteorites can reveal the temperatures and pressures that existed in the early solar system. This information helps us model how planets like Earth came to have their layered structures, crust, mantle, and core. In a way, meteorites are like cosmic textbooks, offering lessons in planetary science that we can't learn any other way. Perhaps most intriguingly, meteorites have sparked a fascinating debate about the origins of life. Some contain complex organic molecules, suggesting that the ingredients for life may have been widespread in the early solar system. Could these meteorites have seeded Earth with the materials needed for life to emerge? It's a compelling idea and one that continues to drive research. As we study these ancient rocks, we're not just uncovering the history of our solar system. We're also exploring the possibility that life itself might have cosmic origins. Meteorites remind us that the universe is far more interconnected than we often realize. They're not just relics of the past, they're messengers carrying stories from the depths of space to our very doorstep. And as we continue to analyze these cosmic visitors, we're not only learning about the origins of our solar system, we're also uncovering clues about our own beginnings. The next time you look up at the night sky, remember, the universe isn't just out there, it's also here in the rocks beneath our feet, waiting to share its secrets. In the vast sea of meteorites that have fallen to Earth, few have captured the imagination of scientists and the public quite like the Allende meteorite. Its arrival on a quiet February night in 1969 was nothing short of spectacular, as it streaked across the skies of northern Mexico, breaking into thousands of fragments. It left behind a trail of cosmic debris scattered over an area the size of a small town. But this wasn't just any meteorite. From the moment it was discovered, researchers knew they were holding something extraordinary. The Allende meteorite wasn't just a rock from space. It was a time capsule, a piece of the solar system's earliest days, preserved for over 4.5 billion years. What makes the Allende meteorite so special is its classification as a carbonaceous chondrite. These rare meteorites are like the fossils of the solar system, containing some of the most primitive materials ever found. Unlike other meteorites, which may have undergone significant changes over time, carbonaceous chondrites like Alende have remained relatively untouched since their formation. They're like snapshots of the solar nebula, the swirling cloud of gas and dust from which the sun and planets emerged. And within Alende, scientists discovered something even more remarkable: calcium aluminum-rich inclusions, or Chi. These tiny crystalline structures are some of the oldest materials ever identified, dating back to the very dawn of our solar system. CAIs are more than just ancient. They're windows into a time when the sun was still a newborn star and the planets were nothing more than specks of dust. Formed in the extreme heat of the early solar nebula, these inclusions contain minerals that condensed directly from the gas cloud, capturing the conditions of that primordial environment. By studying CAIs, scientists have been able to piece together the timeline of the solar system's formation, pinpointing events that occurred just a few million years after the sun's birth. It's like having a cosmic clock, one that ticks back to the very beginning. But the Allende meteorite doesn't just tell us about the past, it also challenges our understanding of how planets form. The presence of CAIs and other ancient materials suggests that the early solar system was far more dynamic and complex than we once thought. For example, the discovery of isotopic anomalies, variations in the chemical makeup of certain elements, has led scientists to reconsider how materials were distributed and mixed in the solar nebula. These findings have reshaped our models of planetary formation, showing that the process wasn't as straightforward as we once believed. Instead, it was a chaotic, turbulent dance of dust, gas, and heat, with materials constantly moving and interacting in ways we're only beginning to understand. Beyond its scientific value, the Allende meteorite has also sparked broader questions about our place in the universe. The fact that such ancient materials can survive billions of years and find their way to Earth is a testament to the interconnectedness of the cosmos. Every fragment of Allende is a reminder that the story of our solar system, and by extension our own story, is written in the stars. As we continue to study this remarkable meteorite, we're not just uncovering the history of the solar system, we're also gaining insights into the processes that shape planets, including our own. The Allende meteorite is more than a scientific curiosity. It's a bridge to our cosmic origins. By examining its ancient grains and crystals, we're piecing together a story that began long before Earth existed. It's a story of chaos and creation, of dust and fire, and of the incredible journey that brought us here. And as we delve deeper into its secrets, we're reminded that the universe isn't just a vast, unknowable void. It's a place filled with stories waiting to be told, stories that connect us to the very fabric of existence. While meteorites and stardust offer tangible glimpses into the cosmos, there's another relic that's far more elusive yet equally fascinating: cosmic dust. Unlike the dramatic arrival of a meteorite or the ancient grains trapped within them, cosmic dust is invisible to the naked eye, drifting silently through the vast emptiness of space. Yet, despite its unassuming nature, this dust plays a monumental role in shaping the universe. It's the quiet builder, the unseen architect of stars, planets, and even life itself. Cosmic dust begins its journey in the fiery final moments of stars. When massive stars reach the end of their lives and explode in supernova, they don't just vanish into nothingness. Instead, they scatter their remains across the galaxy, creating vast clouds of gas and dust. Similarly, smaller stars, as they age and shed their outer layers, contribute to this cosmic reservoir. These tiny particles, often just a fraction of the width of a human hair, are composed of elements like carbon, silicon, and iron materials that will one day become the building blocks of new worlds. But cosmic dust doesn't just linger in the void. It's active, dynamic, and essential. Over millions of years, gravity pulls these dust particles together, gradually forming dense clouds. Within these clouds, the dust begins to clump, creating the seeds of future stars and planets. In a way, cosmic dust is the raw material of creation, the starting point for the birth of everything from the smallest asteroid to the largest galaxy. Without it, the universe as we know it simply wouldn't exist. What's truly remarkable is that we can study this invisible relic without leaving Earth. Scientists have developed ingenious ways to collect cosmic dust, even from our own atmosphere. High-altitude planes equipped with special filters soar through the upper layers of the atmosphere, capturing these microscopic particles as they drift down from space. Other methods involve studying Antarctic ice cores, where cosmic dust has settled over thousands of years, preserved in pristine layers of ice. Each grain tells a story, revealing details about the stars that created it and the journey it took to reach us. But cosmic dust isn't just a relic of the past, it's also a force in the present. It plays a surprising role in shaping our planet's environment. Every year, thousands of tons of cosmic dust fall to Earth, adding to its mass and influencing its chemistry. Some researchers even suggest that this dust could have played a part in seeding Earth with the organic molecules necessary for life. It's a humbling thought that the same dust that forms stars and planets might also have contributed to the emergence of life on our own world. Perhaps the most astonishing aspect of cosmic dust is its sheer ubiquity. It's everywhere in the space between stars, in the atmospheres of planets, and even in the air we breathe. Yet, despite its omnipresence, it often goes unnoticed. It's a reminder that the universe isn't just made up of the grand and the visible, it's also shaped by the tiny and unseen. As we continue to study this invisible relic, we're not just uncovering the secrets of the cosmos, we're also gaining a deeper appreciation for the intricate web of connections that bind us to the stars. Cosmic dust may be small, but its impact is anything but. It's a testament to the fact that even the most unassuming parts of the universe can hold the keys to understanding its greatest mysteries. And as we peer into the vastness of space, we're reminded that the story of the cosmos isn't just written in the light of stars, it's also etched in the dust that drifts between them. The story of cosmic dust isn't just confined to the vast expanse of space, it's also deeply woven into the history of our own planet. Long before life emerged on Earth, this seemingly insignificant dust was already shaping the world we know today. Picture this: billions of years ago, as Earth was still cooling and forming, a steady rain of cosmic dust began to fall from the skies. These tiny particles, invisible to the naked eye, carried with them something extraordinary, the essential ingredients for life. Carbon, water, and even organic molecules may have hitched a ride on this cosmic delivery system, transforming a barren world into a fertile one. One of the most compelling theories about cosmic dust is its role in delivering water to early Earth. Water, as we know, is the foundation of life, but how it arrived on our planet remains a mystery. While some suggest that water came from icy comets, others argue that cosmic dust played a crucial part. These particles, rich in minerals and compounds, could have acted like microscopic sponges, absorbing water molecules as they traveled through space. When they eventually reached Earth, they released this precious resource, slowly filling the planet's oceans over millions of years. It's a remarkable idea that the water we drink today might have origins stretching back to the dust of ancient stars. But cosmic dust didn't just bring water, it may have also delivered the building blocks of life itself. Scientists have discovered that some dust grains contain complex organic molecules, including amino acids, the very compounds that form proteins and DNA. Could these tiny particles have seeded Earth with the materials needed for life to emerge? It's a tantalizing possibility and one that has sparked intense research. Imagine the scene, a young Earth bombarded by cosmic dust, each grain carrying the potential for life. Over time, these molecules could have combined and evolved, setting the stage for the first living organisms. Evidence for this theory can be found in the rocks beneath our feet. Ancient rock layers, some dating back billions of years, contain traces of cosmic dust preserved like time capsules. By analyzing these layers, scientists have uncovered clues about the conditions on early Earth and the role cosmic dust played in shaping them. Similarly, ice cores from places like Antarctica have revealed layers of dust that settled over millennia, offering a snapshot of how much cosmic material has fallen to Earth over time. These studies not only confirm the presence of cosmic dust, but also provide insights into its impact on our planet's history. The implications of cosmic dust go far beyond geology and biology. They touch on the very essence of life itself. If these tiny particles did indeed deliver the ingredients for life, then we are, in a sense, the products of stardust. Every molecule in our bodies, every drop of water we drink, and every breath we take may have cosmic origins. It's a profound connection, one that links us not just to Earth, but to the entire universe. This idea challenges us to rethink our place in the cosmos, to see ourselves not as separate from the stars, but as part of their ongoing story. As we continue to study cosmic dust, we're uncovering more than just the history of Earth. We're piecing together the story of life itself. These tiny particles, once overlooked, are now recognized as vital players in the grand narrative of the universe. They remind us that even the smallest things can have the greatest impact, shaping worlds and sparking life in ways we're only beginning to understand. And as we look to the stars, we're reminded that the universe isn't just out there, it's also here, in the dust beneath our feet, waiting to reveal its secrets. One of the most extraordinary cosmic relics ever discovered fell to Earth on a quiet September morning in 1969, just months after the Allende meteorite made headlines. The Murchison meteorite, named after the small Australian town where it landed, wasn't just another space rock, it was a scientific goldmine, packed with secrets about the origins of life itself. When it streaked through the sky and shattered into hundreds of fragments, no one could have predicted how much it would revolutionize our understanding of the universe. Inside this unassuming chunk of rock lay a treasure trove of organic compounds, including amino acids, sugars, and other molecules essential to life as we know it. This wasn't just a meteorite, it was a message from the cosmos, one that hinted at the possibility that life's building blocks might have been forged in the stars. What makes the Murchison meteorite so remarkable is its classification as a carbonaceous chondrite, much like the Allende meteorite, but Murchison took things a step further. When scientists analyzed its composition, they found over 70 different amino acids, many of which are the same ones used by life on Earth. These molecules, which form the basis of proteins and DNA, are crucial for the development of living organisms. Yet here they were, preserved in a rock that had traveled through space for billions of years. The discovery was groundbreaking. It suggested that the ingredients for life might not be unique to Earth but could instead be scattered throughout the universe, waiting for the right conditions to spark life into existence. The implications of this finding are profound. If amino acids and other organic compounds can form in space and survive the journey to Earth, then life's origins might not be as Earth-centric as we once thought. Instead of emerging solely from the planet's primordial soup, life could have been kickstarted by materials delivered from the cosmos. This idea, known as Panspermia, raises the tantalizing possibility that life is a universal phenomenon, not confined to our planet. The Murchison meteorite became a cornerstone of this theory, offering tangible evidence that the building blocks of life are not only common in the universe but also incredibly resilient. But the story doesn't end there. In recent years, researchers have made even more astonishing discoveries within the Murchison meteorite. They've identified complex sugars, including ribose, a key component of RNA, the molecule essential for storing and transmitting genetic information. This finding adds another layer to the puzzle, suggesting that the precursors to life's most fundamental processes might also have extraterrestrial origins. Each new discovery within this meteorite deepens our understanding of how life could arise, not just on Earth, but potentially on other worlds as well. The Murchison meteorite has also become a focal point for astrobiology, the study of life's potential beyond Earth. By analyzing its organic compounds, scientists are learning how these molecules form, survive, and interact in the harsh environment of space. This knowledge is crucial as we search for signs of life elsewhere in the solar system, from the icy moons of Jupiter and Saturn to the dusty plains of Mars. The meteorite serves as a reminder that the universe is brimming with possibilities, and that life, in some form, might be far more widespread than we ever imagined. As we continue to study the Murchison meteorite, we're not just uncovering the history of a single rock, we're piecing together the story of life itself. Its organic compounds are like cosmic breadcrumbs, leading us closer to answering one of humanity's oldest questions. Are we alone in the universe? While we don't yet have a definitive answer, the Murchison meteorite has given us reason to hope and to keep searching. After all, if the ingredients for life can travel across the stars, then perhaps life itself is out there, waiting to be discovered. The Murchison meteorite isn't just a relic of the early solar system, it's a key to one of the most profound questions humanity has ever asked. How did life begin? This ancient rock, filled with amino acids and other organic molecules, offers a tantalizing glimpse into the possibility that life's building blocks didn't originate on Earth at all. Instead, they may have been delivered from the stars, carried here by comets, meteorites, or even cosmic dust. This idea, known as the Panspermia hypothesis, challenges our traditional view of life's origins and opens up a universe of possibilities. At its core, Panspermia suggests that the ingredients for life are not unique to Earth but are scattered throughout the cosmos. The discovery of complex organic molecules in meteorites like Murchison lends strong support to this theory. These molecules, which include amino acids and sugars, are the very foundation of life as we know it. Finding them in space suggests that the universe might be teeming with the raw materials needed to spark life, waiting for the right conditions to bring it to fruition. It's a humbling thought that life on Earth might owe its existence, at least in part, to the stars themselves. But how could these fragile molecules survive the harsh journey through space? The answer lies in the resilience of cosmic relics. Meteorites, for example, act as protective capsules, shielding their precious cargo from the extremes of radiation and temperature. When they enter Earth's atmosphere, their outer layers burn away, but the material inside remains intact, delivering its ancient payload to the surface. Similarly, comets, which are essentially icy time capsules, could have carried organic molecules across vast distances, depositing them on our planet during collisions. These cosmic couriers may have played a crucial role in seeding Earth with the ingredients for life. The evidence for Panspermia isn't limited to meteorites and comets. Telescopes and space probes have detected complex organic molecules in the most unexpected places, floating in the clouds of distant nebulae, embedded in the icy surfaces of moons, and even in the atmospheres of other planets. These discoveries suggest that the building blocks of life are not rare or confined to Earth, but are instead a common feature of the cosmos. If life's ingredients are so widespread, then the conditions needed to spark life might be more common than we once believed. This raises a fascinating question. If life's building blocks are universal, could life itself be universal? The Panspermia hypothesis doesn't just challenge our understanding of life's origins, it also reshapes our view of its potential. If the seeds of life can travel across the stars, then it's possible that life has emerged not just on Earth, but on countless other worlds. This idea has profound implications for astrobiology, the search for life beyond our planet. It suggests that we might not need to look far to find evidence of life, or at least its precursors elsewhere in the solar system. From the icy oceans of Europa to the methane lakes of Titan, the ingredients for life might already be there, waiting to be discovered. Yet, Panspermia is not without its skeptics. Some argue that while the delivery of organic molecules is possible, the leap from these molecules to living organisms is still a mystery. Others point out that the conditions on early Earth, such as its atmosphere, temperature, and chemical composition, played a crucial role in transforming these molecules into life. These challenges remind us that while cosmic relics provide tantalizing clues, they are just one piece of a much larger puzzle. The origins of life remain one of science's greatest mysteries, and it will take more than meteorites to solve it. What cosmic relics like the Murchison meteorite do offer, however, is a sense of connection, a reminder that the story of life is not just an earthly tale but a cosmic one. They invite us to look beyond our planet and consider the possibility that life, in some form, might be woven into the fabric of the universe itself. As we continue to explore the cosmos, these ancient artifacts will guide us, offering clues about where we came from and perhaps where life might exist next. While meteorites and cosmic dust offer us fragments of the universe's distant past, some of the most revealing relics come from much closer to home. On worlds like the Moon and Mars, rocks have survived for billions of years, untouched by the geological processes that constantly reshape Earth's surface. These ancient stones are more than just remnants of the solar system's infancy. They're time capsules preserving a record of the chaos and creation that defined our cosmic neighborhood in its earliest days. Among them are some of the oldest rocks ever discovered, older than anything found on Earth, and they hold secrets that could rewrite our understanding of planetary evolution. Take the Moon, for example. During the Apollo missions, astronauts collected hundreds of pounds of lunar rocks and soil, bringing them back to Earth for analysis. Among these samples were rocks dating back over 4 billion years, making them some of the oldest materials ever studied. These ancient lunar rocks, formed during a time when the Moon was still cooling from its fiery birth, provide a snapshot of the solar system's youth. By studying their composition, scientists have learned that the Moon was once a molten ocean of magma, its surface constantly bombarded by asteroids and comets. These impacts didn't just shape the moon, they also left behind clues about the conditions of the early solar system. One of the most remarkable discoveries came from the Apollo 17 mission, which returned a sample known as the Genesis rock. This rock, nearly 4.5 billion years old, is thought to have formed during the moon's crustal solidification. Its pristine condition and ancient age make it a cornerstone of lunar geology, offering insights into how the moon, and by extension, Earth evolved from a molten state to the worlds we know today. The Genesis rock is a testament to the moon's role as a cosmic archive, preserving a record of events that have long since vanished from Earth's surface. But the moon isn't the only place where ancient rocks have been found. On Mars, rovers like Curiosity and Perseverance have uncovered rocks that date back to the planet's earliest days. These Martian rocks, some of which are over 4 billion years old, reveal a world that was once far more Earth-like, with flowing rivers, lakes, and possibly even oceans. By studying these rocks, scientists have pieced together a timeline of Mars's geological history, showing how it transitioned from a warm, wet world to the cold, arid planet we see today. These findings don't just tell us about Mars, they also offer clues about how rocky planets, including Earth, form and change over time. So how do scientists determine the age of these ancient rocks? The answer lies in radiometric dating, a technique that measures the decay of radioactive isotopes within the rock. When a rock forms, it contains a certain amount of radioactive elements like uranium or potassium. Over time, these elements decay into stable isotopes at a known rate, acting like a natural clock. By measuring the ratio of the original radioactive element to its decay products, scientists can calculate the rock's age with remarkable precision. This method has allowed researchers to date lunar and Martian rocks as well as meteorites, giving us a detailed timeline of the solar system's formation. The importance of studying these ancient rocks goes beyond mere curiosity. They provide a window into the processes that shaped not just individual planets but the entire solar system. For example, the heavy bombardment period, a time when the inner planets were pummeled by asteroids and comets, is recorded in the scars and craters of the Moon and Mars. These impacts didn't just shape the surfaces of these worlds, they also delivered water and organic molecules, potentially setting the stage for life. By studying these rocks, we're not just looking back in time, we're exploring the forces that made life on Earth possible. What's truly fascinating is how interconnected these ancient rocks make the solar system seem. The same processes that shaped the Moon and Mars also shaped Earth, and the same materials that formed these worlds are found in meteorites and cosmic dust. By studying these relics, we're piecing together a story that spans billions of years, a story of collision, creation, and transformation. Each rock, whether from the Moon, Mars, or beyond, is a chapter in this cosmic tale, helping us understand not just where we came from, but how we fit into the broader universe. As we continue to explore these ancient worlds, we're reminded that the past is not just history, it's a guide. These rocks, older than life itself, hold the keys to understanding the forces that shaped our solar system and ultimately our own existence. They're a reminder that the universe is not just a place of vast emptiness, but a dynamic, ever-changing system filled with stories waiting to be uncovered. And as we delve deeper into these ancient relics, we're not just uncovering the past, we're charting the future of our understanding of the cosmos. Among the most extraordinary cosmic relics ever collected are the lunar samples brought back by the Apollo missions. These rocks, gathered from the Moon's surface, are more than just souvenirs from another world. They're time capsules, preserving a record of the Moon's violent birth and its early evolution. When astronauts first stepped onto the lunar surface, they weren't just exploring a new frontier. They were unearthing pieces of a story that began over 4 billion years ago, a story that holds the key to understanding not just the moon, but our own planet as well. The moon's formation is a tale of cosmic chaos. Around 4.5 billion years ago, a Mars-sized object collided with the young Earth in a cataclysmic event that reshaped both worlds. The debris from this collision eventually coalesced to form the moon, but the process was anything but gentle. The newly formed moon was a molten inferno, its surface a churning ocean of magma. As it cooled, this magma ocean began to solidify, forming the first layers of the lunar crust. The rocks collected by Apollo astronauts capture this early chapter in the moon's history, offering a glimpse into a time when our closest neighbor was still a fiery, turbulent world. One of the most significant discoveries from these lunar samples is the presence of anorthosite, a type of rock that formed as the magma ocean cooled. Anorthosite is lightweight and buoyant, which allowed it to float to the surface of the magma, creating the moon's first crust. By studying these rocks, scientists have pieced together a timeline of the moon's cooling process, showing how it transitioned from a molten mass to the solid, cratered world we see today. These findings don't just tell us about the moon, they also shed light on the early history of Earth, which underwent a similar process of cooling and crust formation. But the moon's story doesn't end with its magma ocean. The lunar surface bears the scars of countless impacts, evidence of a time when the solar system was a far more violent place. During a period known as the Late Heavy Bombardment, the moon and Earth were pummeled by asteroids and comets, leaving behind massive craters and reshaping the surfaces of both worlds. The rocks collected by Apollo astronauts contain fragments of this chaotic era, including breccias rocks made up of broken fragments fused together by the heat and pressure of impacts. These breccias are like geological mosaics, each piece telling a story of a different impact, a different moment in the moon's turbulent past. What makes these lunar samples so valuable is their ability to help us reconstruct the history of the Earth-Moon system. Because Earth's surface is constantly reshaped by erosion, plate tectonics, and other geological processes, much of its early history has been erased. But the moon, with its lack of atmosphere and geological activity, has preserved a pristine record of its past. By studying lunar rocks, scientists can infer what Earth was like during its earliest days, from the composition of its atmosphere to the frequency of impact. In a sense, the moon acts as a mirror, reflecting the history of our own planet in ways we couldn't see otherwise. The implications of studying lunar relics extend far beyond the moon itself. These rocks have helped scientists refine their understanding of planetary formation, showing how worlds evolve from molten masses to stable, solid bodies. They've also provided insights into the origins of water and other volatiles, which may have been delivered to both the moon and Earth by impacting comets. By piecing together the moon's history, we're not just learning about a distant world, we're uncovering the processes that shaped our own. As we continue to explore the moon, both through past missions and future endeavors, these ancient rocks will remain a vital source of knowledge. They remind us that the moon isn't just a silent companion in the night sky. It's a dynamic world with a rich history, one that's deeply intertwined with our own. And as we study these cosmic relics, we're not just uncovering the past, we're gaining a deeper appreciation for the forces that shaped our place in the universe. Among the countless meteorites that have fallen to Earth, a select few stand out as messengers from another world, Mars. Known as Martian meteorites, these rare cosmic relics are pieces of the red planet itself, ejected into space by violent impacts and eventually finding their way to Earth. Imagine holding a piece of Mars in your hand, a fragment of a world millions of miles away, carrying secrets from its ancient past. These meteorites are more than just rocks. They're time capsules offering us a direct link to Mars' geological history and perhaps even clues about the possibility of life beyond our planet. The journey of a Martian meteorite begins with a cataclysmic event, a massive asteroid or comet slamming into Mars with enough force to blast debris into space. Some of these fragments, traveling through the void for millions of years, eventually cross paths with Earth, burning through the atmosphere and landing as meteorites. Of the tens of thousands of meteorites found on Earth, only a handful fewer than 300 have been identified as Martian. Their unique composition, which matches the data gathered by Mars rovers and orbiters, confirms their origin. These meteorites are like cosmic postcards, carrying a message from a world we've only begun to explore. One of the most famous Martian meteorites is LH 84001, discovered in Antarctica in 1984. This ancient rock, estimated to be over 4 billion years old, made headlines in the 1990s when scientists announced the discovery of microscopic structures that resembled fossilized bacteria. Could these structures be evidence of ancient Martian life? The announcement ignited a firestorm of debate, with some researchers convinced they had found proof of extraterrestrial life, while others remained skeptical, arguing that the structures could have formed through non-biological processes. Though the debate remains unresolved, LH 84001 sparked a renewed interest in the search for life on Mars and opened up new avenues of research. What makes Martian meteorites so valuable is their ability to provide insights into Mars' geological and climatic history. By studying their mineral composition, scientists have learned that Mars was once a much warmer and wetter world, with flowing rivers, lakes, and possibly even oceans. Some meteorites contain minerals that form in the presence of water, offering tantalizing clues about the planet's past habitability. Others reveal evidence of volcanic activity, suggesting that Mars was once a geologically active world, much like Earth. These findings paint a picture of a dynamic planet, one that may have once been capable of supporting life. But the study of Martian meteorites isn't just about the past, it's also about the future. As we prepare for human missions to Mars, understanding the planet's geology and climate is crucial. Martian meteorites provide a unique opportunity to study the red planet's surface without leaving Earth, helping scientists identify potential landing sites and resources for future explorers. They also offer a glimpse into the challenges astronauts might face, from the planet's thin atmosphere to its harsh, radiation-filled environment. In a sense, these meteorites are like scouts, paving the way for humanity's next great adventure. The search for life on Mars is one of the most compelling questions in science, and Martian meteorites are at the heart of this quest. While LH 84001 remains controversial, it has inspired a new generation of researchers to explore the possibility that life once existed, or may still exist on the red planet. Recent missions like NASA Perseverance rover are building on this legacy, searching for signs of ancient life in Martian rocks and soil. Whether or not life is ever found, the study of Martian meteorites will continue to deepen our understanding of Mars and its potential to harbor life. Martian meteorites remind us that the story of our solar system is one of connection. Just as Earth and Mars share a common history, so too do these rocks connect us to a world that has long captured our imagination. They're a reminder that the universe is full of surprises, and that even the smallest fragment of rock can hold the key to unlocking its greatest mysteries. As we continue to explore these cosmic relics, we're not just uncovering the history of Mars, we're also taking a step closer to answering one of humanity's oldest questions: are we alone in the universe? The search for life on Mars is far from over, and each new discovery brings us closer to understanding whether the red planet was once a cradle of life. From the microscopic structures in ALH 84001 to the minerals that hint at ancient water, Martian meteorites are guiding us on this journey. They're a testament to the power of curiosity and a reminder that the universe is full of stories waiting to be told. And as we look to the stars, we're reminded that the answers we seek might be closer than we think, hidden in the rocks beneath our feet and the skies above. The possibility of ancient life on Mars has long captivated scientists and dreamers alike. This tantalizing question isn't just about the red planet. It's about understanding whether life is a rare fluke or a common thread woven throughout the cosmos. Cosmic relics from Mars, particularly Martian meteorites, have played a pivotal role in this search, offering clues about the planet's past and its potential to support life. These rocks, ejected from Mars during violent impacts and journeying across space to Earth, are more than just fragments of another world. They're pieces of a puzzle that could reshape our understanding of life itself. One of the most compelling pieces of evidence for past life on Mars is the presence of water. For decades, missions to the red planet have revealed signs of ancient rivers, lakes, and even oceans. Martian meteorites have added weight to these discoveries. Some of these rocks contain minerals that only form in the presence of water, like clays and carbonates. Others bear tiny droplets of liquid trapped within them, offering a snapshot of the watery conditions that may have once existed on Mars. These findings paint a picture of a planet that was not only wet but potentially habitable, with conditions that could have supported microbial life billions of years ago. But water alone isn't enough to prove life existed or still exists on Mars. Scientists are also looking for organic molecules, the building blocks of life. Martian meteorites have delivered these as well. Some contain complex organic compounds, including amino acids and even sugars, suggesting that the ingredients for life were present on Mars long ago. While these molecules don't prove life existed, they do indicate that the red planet had the necessary materials to spark it. This raises a profound question. If Mars had water, organic molecules, and a stable environment, could life have taken root there? The answer, though still unknown, feels tantalizingly close. The implications of finding ancient life on Mars are staggering. If life once thrived on the red planet, it would suggest that life is not unique to Earth but a universal phenomenon. This idea, known as Panspermia, proposes that life's building blocks could travel between planets carried by meteorites or comets. If true, it would mean that life on Earth might have extraterrestrial origins, seeded by materials from Mars or elsewhere in the solar system. The discovery of Martian meteorites packed with organic compounds has given this theory new momentum, offering a plausible pathway for life to spread across the cosmos. Yet, the search for ancient life on Mars is far from simple. The harsh conditions on the planet's surface, intense radiation, freezing temperatures, and a thin atmosphere make it a challenging place for life to survive, let alone thrive. Even if life did exist in the past, finding direct evidence of it is like searching for a needle in a cosmic haystack. That's where Martian meteorites come in. These rocks, which have been shielded from the worst of Mars' surface conditions, provide a unique opportunity to study the planet's potential for life without the need for a return mission. By analyzing their composition, scientists can identify the conditions that once made Mars habitable and search for signs of ancient biology. The broader implications of this search extend far beyond Mars. If life could arise independently on two neighboring planets, it raises the possibility that it could exist elsewhere in the universe. This idea has fueled the search for life on icy moons like Europa and Enceladus, on distant exoplanets, and even in the clouds of gas giants. Each discovery, whether from Mars or beyond, brings us closer to answering one of humanity's oldest questions: are we alone? The study of Martian meteorites is not just about understanding the red planet. It's about uncovering the universal principles that govern life itself. As we continue to explore Mars, both through meteorites and missions like NASA's Perseverance rover, we're not just searching for ancient life, we're redefining what it means to be alive. The possibility that life could exist beyond Earth challenges us to think bigger, to see ourselves not as isolated beings but as part of a vast, interconnected cosmos. Every rock, every molecule, and every discovery brings us closer to understanding our place in the universe. And as we look to the stars, we're reminded that the answers we seek might be closer than we think, hidden in the ancient relics of a world that once mirrored our own. Among the most captivating cosmic relics are comets' frozen time capsules from the outer reaches of our solar system. Unlike the rocky meteorites or the ancient stardust we've explored so far, comets are icy wanderers, preserving some of the most pristine materials from the solar system's infancy. These icy bodies, often referred to as dirty snowballs, are more than just spectacular celestial objects. They're windows into a time when the solar system was still taking shape, holding secrets about the origins of planets, water, and even life itself. Comets formed billions of years ago in the cold, dark regions of the solar system, far beyond the reach of the sun's warmth. In these frigid outskirts, volatile compounds like water, carbon dioxide, and methane froze solid, mixing with dust and rocky particles to create the building blocks of comets. Because they've spent most of their existence in these distant, icy realms, comets have remained largely untouched since their formation. This makes them some of the most pristine relics of the early solar system, preserving a snapshot of the raw materials that existed before planets like Earth took shape. One of the most groundbreaking missions to study comets was the European Space Agency's Rosetta mission, which rendezvoused with comet 67P/Churyumov-Gerasimenko in 2014. For the first time in history, a spacecraft not only orbited a comet but also deployed a lander, Philae, to its surface. The data Rosetta gathered revealed a treasure trove of information about the comet's composition, including the presence of organic molecules like glycine, an amino acid essential for life. This discovery was a game-changer, suggesting that the building blocks of life might be widespread in the cosmos, carried by comets across the solar system. Equally significant was NASA's Stardust mission, which flew through the tail of Comet Wild 2 in 2004, collecting dust particles and returning them to Earth. These tiny grains, analyzed in laboratories around the world, contained a wealth of organic compounds, including complex hydrocarbons. The findings from Stardust reinforced the idea that comets are more than just icy relics. They're cosmic delivery systems, potentially responsible for bringing the ingredients for life to Earth and other planets. But comets aren't just about organic molecules. They also play a crucial role in delivering water to terrestrial planets like Earth. The early solar system was a chaotic place, with planets forming in a dry, inhospitable environment close to the sun. So how did Earth end up with so much water? One leading theory is that comets rich in ice bombarded the young planet, depositing water and other volatiles. While some of this water would have been lost to space, much of it remained, eventually forming the oceans and lakes that make life on Earth possible. This idea is supported by the composition of comets themselves. When Rosetta analyzed the water on comet 67P, it found that the ratio of hydrogen isotopes in the comet's water was different from that in Earth's oceans. This suggests that while comets may have contributed to Earth's water supply, they weren't the sole source. Instead, a combination of comets, asteroids, and other cosmic materials likely delivered the water that now covers over 70% of our planet's surface. The study of comets isn't just about understanding the past, it's also about exploring the possibilities of the future. As we continue to study these icy relics, we're gaining insights into the processes that shaped our solar system and the potential for life elsewhere in the universe. Comets remind us that the cosmos is a dynamic, interconnected system, where even the smallest objects can have a profound impact on the evolution of planets and the emergence of life. As we look to the skies, comets serve as a reminder of the mysteries that still await us. These frozen travelers, born in the cold outer reaches of the solar system, carry with them the story of our cosmic origins. And as we continue to explore them, we're not just uncovering the history of the solar system, we're also taking a step closer to understanding our place within it. When we think about Earth's vast oceans, it's easy to take their existence for granted. But have you ever wondered how all that water got here in the first place? One of the most fascinating theories suggests that comets, those icy wanderers from the outer solar system, played a starring role in delivering water to our young planet. This idea isn't just a wild guess, it's backed by science, and it opens up a compelling chapter in the story of how Earth became the blue, life-filled world we know today. The theory goes like this: when Earth first formed over 4.5 billion years ago, it was a hot, molten mess. Any water that might have been present would have boiled away into space, leaving the planet dry and barren. But over time, something changed. Water began to accumulate, eventually forming the oceans that now cover over 70% of Earth's surface. So, where did this water come from? One possibility is that it was delivered by comets' icy bodies rich in water and other volatile compounds. As these comets bombarded the young Earth, they released their frozen cargo, gradually filling the planet's basins with water. But how do we know this theory holds water, so to speak? One key piece of evidence comes from the isotopic composition of water. Water molecules are made up of hydrogen and oxygen, but not all hydrogen atoms are the same. Some are heavier, containing an extra neutron, and are known as deuterium. The ratio of deuterium to normal hydrogen in water can act like a fingerprint, revealing its origins. When scientists analyzed the water in comets like 67P/Churyumov-Gerasimenko, they found that the deuterium to hydrogen ratio didn't quite match that of Earth's oceans. This discrepancy suggests that while comets may have contributed to Earth's water supply, they weren't the only source. This discovery has sparked a lively debate among scientists. If comets didn't deliver all of Earth's water, then where did the rest come from? Some researchers point to asteroids, which are rich in water-bearing minerals. These rocky bodies, closer to the Sun and less volatile than comets, could have played a significant role in delivering water to Earth. Others suggest that Earth's water may have been present all along, locked deep within the planet's interior and released through volcanic activity over millions of years. The truth likely lies somewhere in between, with comets, asteroids, and Earth's own geology all contributing to the planet's watery abundance. Studying comets isn't just about solving the mystery of Earth's water. It's also about understanding how water is distributed throughout the solar system. Comets, with their icy cores and long, looping orbits, act as cosmic couriers, transporting water and other volatiles from the outer solar system to the inner planets. By analyzing the composition of comets, scientists can piece together a map of how water moves through the solar system, shedding light on the processes that make planets like Earth habitable. The implications of this research extend far beyond our own planet. If comets played a role in delivering water to Earth, could they have done the same for other worlds? Mars, for example, shows clear signs of ancient water, from dried-up riverbeds to minerals that only form in the presence of liquid water. Could comets have been responsible for these features as well? And what about icy moons like Europa and Enceladus, which are thought to have vast oceans beneath their frozen surfaces? Understanding the role of comets in delivering water to Earth could help us answer these questions, offering clues about the potential for life elsewhere in the solar system. The story of Earth's water is a reminder of how interconnected our solar system truly is. Comets, born in the cold outer reaches, have traveled billions of miles to shape the destiny of planets like Earth. As we continue to study these icy messengers, we're not just uncovering the history of our own world, we're also gaining insights into the broader processes that make planets habitable. Whether comets were the sole source of Earth's water or just one piece of the puzzle, their role in shaping our planet and potentially others is a testament to the dynamic, ever-changing nature of the cosmos. As we look to the skies, comets remind us that the universe is full of surprises. These ancient travelers, carrying the seeds of life and the mysteries of the past, continue to inspire us to explore, question, and wonder. And as we unravel their secrets, we're not just learning about the origins of water, we're uncovering the story of how life itself came to flourish on our pale blue dot. While most cosmic relics we've explored so far hail from our own solar system, some visitors come from much farther away, other star systems entirely. These interstellar travelers, like the enigmatic Oumuamua and the comet 2I/Borisov, are more than just space rocks. They're messengers from distant corners of the galaxy, offering us a rare glimpse into the cosmic neighborhood beyond our sun. Their discovery has ignited a wave of excitement among scientists and stargazers alike, not just because they're rare, but because they carry secrets about the formation and composition of other star systems. Imagine holding a piece of another solar system in your hands, a fragment of a world trillions of miles away. That's the kind of opportunity these interstellar visitors present. The first of these visitors to make headlines was Oumuamua, discovered in October 2017. This strange, elongated object was unlike anything astronomers had ever seen. Its unusual shape, rapid speed, and lack of a visible tail set it apart from typical comets or asteroids. Initially, some even speculated it could be an alien spacecraft, though further observations suggested a more natural origin. What made Oumuamua so fascinating was its trajectory. It was clearly not bound by the sun's gravity, meaning it had come from outside our solar system. This was the first time humanity had identified an interstellar object passing through our cosmic backyard, and it opened up a whole new field of study. Just 2 years later, another interstellar visitor arrived, Comet 2I/Borisov. Unlike Oumuamua, Borisov looked much more like a traditional comet, with a bright tail and a glowing coma as it approached the sun. This gave scientists a clearer chance to study its composition, revealing gases and dust that hinted at conditions in its home star system. The discovery of Borisov confirmed that Oumuamua wasn't a fluke. Interstellar objects were passing through our solar system more often than we'd realized. What's more, these visitors offered a unique opportunity to compare the materials from other star systems with those in our own, providing a kind of cosmic benchmark for planetary formation. Studying these interstellar relics, however, is no easy task. By the time we detect them, they're often already on their way out of the solar system, moving at incredible speeds. This leaves scientists with a narrow window to gather data, using everything from ground-based telescopes to space observatories. Even with advanced technology, the fleeting nature of these objects makes it challenging to capture detailed information. Yet, every bit of data we collect is invaluable, offering clues about the chemistry, structure, and history of other star systems. For instance, the organic compounds found in 2I/Borisov suggest that the building blocks of life might be common throughout the galaxy, not just in our own solar system. What makes these interstellar visitors so significant isn't just their rarity, it's what they tell us about the universe's diversity. Every star system is thought to have its own unique conditions, shaped by the composition of its protoplanetary disk and the chaotic processes of planet formation. By studying objects like Oumuamua and 2I/Borisov, we're essentially sampling the raw materials of other systems, learning how they differ from our own. This helps us refine our understanding of how planets form, not just here, but everywhere in the galaxy. It's like getting a sneak peek at the cosmic recipe book, showing us the variety of ingredients that can go into making a solar system. The broader implications of these discoveries are profound. If interstellar objects are more common than we once thought, they could serve as natural probes, carrying information about distant star systems across the galaxy. They also raise intriguing questions about the exchange of materials between systems. Could comets or asteroids from other stars have delivered water, organic molecules, or even life to Earth billions of years ago? It's a tantalizing possibility, one that underscores the interconnectedness of the cosmos. These interstellar visitors remind us that our solar system is just one small part of a much larger, dynamic universe filled with stories waiting to be uncovered. As we continue to explore these cosmic travelers, we're not just learning about other star systems, we're also gaining a deeper appreciation for the vastness and complexity of the universe. Each interstellar object is a reminder that the cosmos is teeming with mysteries, and that even the smallest, fastest-moving fragments can hold the keys to unlocking its greatest secrets. The next time you look up at the night sky, remember, out there among the stars are countless relics from distant worlds, each with its own story to tell. And as we study them, we're taking a step closer to understanding not just where we came from, but how we fit into the grand tapestry of the universe. When Oumuamua first appeared in our solar system in 2017, it didn't just catch the attention of astronomers, it sparked a global fascination. This strange, cigar-shaped object was unlike anything we'd ever seen. Tumbling through space at incredible speeds, it didn't behave like a typical comet or asteroid. No tail of gas or dust trailed behind it, and its trajectory suggested it wasn't bound by the sun's gravity. Instead, it seemed to be a visitor from another star system, the first of its kind ever detected. Almost immediately, the questions began. What was Oumuamua and where had it come from? One of the most striking features of Oumuamua was its unusual shape. While most asteroids and comets are roughly spherical or lumpy, Oumuamua was elongated, stretching over 800 feet in length but only about 80 feet wide. This extreme shape, combined with its rapid rotation, made it unlike any natural object we'd observed before. Adding to the mystery was its trajectory. As it sped through the solar system, it didn't follow the predictable path of an object influenced solely by gravity. Instead, it appeared to accelerate slightly, as if something was pushing it forward. This unexpected behavior led to a flurry of hypotheses, from the mundane to the extraordinary. Some scientists proposed that Oumuamua could be a fragment of a larger object, perhaps shattered by a collision in its home star system. Others suggested it might be a chunk of frozen hydrogen or nitrogen, which could explain its lack of a visible tail and its slight acceleration as it sublimated in the sun's heat. But the most tantalizing theory, and the one that captured the public's imagination, was the idea that Oumuamua might be artificial. Could it be a piece of alien technology, perhaps a solar sail or a derelict spacecraft? While this possibility remains speculative, it's a reminder of how little we know about the objects that drift between stars. What makes Oumuamua so important isn't just its mystery, it's what it taught us about the universe. Its discovery confirmed that interstellar objects pass through our solar system more frequently than we'd thought, offering us a chance to study materials from other star systems up close. By analyzing its light and trajectory, scientists gained insights into its composition and motion, even though it was moving too fast to capture detailed images. These observations have helped refine our understanding of how such objects form and travel, shedding light on the processes that shape planetary systems beyond our own. The search for interstellar objects has only intensified since Oumuamua's visit. With advancements in telescope technology, astronomers are now better equipped to detect these fleeting visitors, giving us a chance to study them in more detail. Each new discovery adds to our understanding of the cosmos, revealing the diversity of materials and conditions that exist in other star systems. These objects are like cosmic postcards, carrying messages from distant worlds and offering clues about the universe's vast complexity. As we continue to explore the mysteries of Oumuamua and other interstellar visitors, we're reminded of how much there is still to learn. These objects challenge our assumptions, spark our curiosity, and push the boundaries of what we thought was possible. They remind us that the universe is full of surprises, and that even the smallest, fastest-moving fragments can hold the keys to unlocking its greatest secrets. The next time you look up at the night sky, remember, out there among the stars are countless relics from distant worlds, each with its own story to tell. And as we study them, we're taking a step closer to understanding not just where we came from, but how we fit into the grand tapestry of the universe. While Oumuamua captivated the world with its mysterious origins and peculiar behavior, it wasn't the only interstellar visitor to grace our solar system. Just 2 years later, astronomers spotted another traveler from beyond the stars 2I/Borisov. Unlike its enigmatic predecessor, Borisov looked far more familiar, with a glowing coma and a long, sweeping tail that marked it as a classic comet. But don't let its appearance fool you. This icy wanderer wasn't from our solar system. It was a visitor from another star, offering us an unprecedented chance to study the raw materials of a distant planetary system. The discovery of 2I/Borisov in August 2019 was a game-changer. Unlike Oumuamua, which was already on its way out of the solar system by the time we noticed it, Borisov gave scientists a longer window to observe and analyze its composition. As it approached the sun, its icy surface began to vaporize, releasing gases and dust that formed its distinctive tail. This outgassing allowed astronomers to study its chemical makeup in detail, revealing a treasure trove of information about its origins. What they found was fascinating. Borisov contained carbon monoxide, hydrogen cyanide, and other molecules commonly found in comets within our own solar system. Yet, the ratios of these compounds were subtly different, hinting at unique conditions in its home star system. One of the most striking aspects of Borisov was how much it resembled the comets we're familiar with, yet how distinctly alien it was at the same time. For instance, while its chemical composition was similar to that of our solar system's comets, the amount of carbon monoxide it released was far higher than anything we've seen before. This suggests that Borisov formed in an extremely cold environment, far colder than the regions where most comets in our system originate. It's a reminder that while the building blocks of planetary systems might be universal, the conditions under which they form can vary dramatically from one star system to another. Studying 2I/Borisov has provided invaluable insights into how planetary systems form and evolve. By comparing its composition to that of comets in our own solar system, scientists can identify which features are unique to our cosmic neighborhood and which are universal. For example, the presence of organic molecules in Borisov reinforces the idea that the ingredients for life, or at least its precursors, are widespread throughout the galaxy. This discovery has profound implications for astrobiology, suggesting that the potential for life might not be limited to Earth or even our solar system. But the significance of Borisov goes beyond its chemical composition. Its very existence tells us that interstellar objects are far more common than we once thought. Before Oumuamua and Borisov, the idea of objects from other star systems passing through our solar system was largely theoretical. Now we have concrete evidence that these visitors are a regular occurrence, opening up new avenues for research. Future telescopes like the Vera C. Rubin Observatory are expected to detect many more interstellar objects, giving us a clearer picture of the diversity of materials and conditions in other star systems. The implications of these discoveries extend far beyond astronomy. They challenge us to rethink our place in the universe and the interconnectedness of all cosmic systems. If comets like Borisov can travel between stars, could they have delivered water, organic molecules, or even life to Earth billions of years ago? It's a tantalizing possibility, one that blurs the lines between our solar system and the broader galaxy. By studying these interstellar visitors, we're not just learning about distant star systems, we're uncovering the processes that might have shaped life on our own planet. As we look to the future, the study of interstellar objects like 2I/Borisov will play a crucial role in our exploration of the cosmos. These visitors are like cosmic ambassadors, carrying messages from distant worlds and offering us a glimpse into the vast, interconnected tapestry of the universe. Each discovery brings us closer to understanding not just where we came from, but how we fit into the grand story of the cosmos. And as we continue to explore, we're reminded that the universe is full of surprises, waiting to be uncovered by those who dare to look. As we've journeyed through the mysteries of cosmic relics from ancient stardust to Martian meteorites, one question remains: how do we uncover more of these interstellar treasures? The search for relics from beyond our solar system is one of the most exciting frontiers in astronomy, but it's also one of the most challenging. These objects, born in distant star systems, are fleeting visitors to our cosmic neighborhood, often detected only as they speed past us on their way back into the void. Yet, every discovery offers a chance to piece together the story of the universe beyond our own backyard. One of the biggest hurdles in finding interstellar relics is their sheer speed and unpredictability. Unlike objects bound by the sun's gravity, these visitors move at incredible velocities, often crossing the entire solar system in a matter of months. By the time we spot them, they're already on their way out, leaving astronomers with a narrow window to gather data. This fleeting nature makes detection a race against time, requiring a combination of cutting-edge technology and precise coordination. Ground-based telescopes like the Pan-STARRS system in Hawaii play a crucial role in scanning the skies for these fast-moving objects. Their wide-field cameras capture vast swaths of the night sky, allowing astronomers to identify anything unusual, whether it's a faint streak of light or a blurry dot moving against the backdrop of stars. But spotting an interstellar object is just the first step. Once detected, the real work begins, studying its composition, trajectory, and behavior. This is where space-based observatories like the Hubble Space Telescope come into play. With their ability to capture high-resolution images and spectra, these instruments allow scientists to analyze the light reflected or emitted by these objects, revealing clues about their chemical makeup and structure. For example, when 2I/Borisov passed through our solar system, Hubble's observations provided detailed insights into its tail and coma, helping scientists understand how it compared to comets from our own system. Despite these advancements, there's still so much we don't know. Interstellar objects are rare, and each one we study raises as many questions as it answers. What makes them so different from the objects in our solar system? How do they form, and what can they tell us about the conditions in their home star systems? To answer these questions, astronomers are pushing for more ambitious missions, ones that could intercept these visitors and study them up close. Imagine a spacecraft equipped with state-of-the-art instruments, rendezvousing with an interstellar object as it passes through our solar system. Such a mission could provide unprecedented insights into the materials and processes that shape other star systems, offering a first-hand look at the universe's diversity. The implications of these discoveries go far beyond astronomy. By studying interstellar relics, we're not just learning about distant worlds, we're gaining a deeper understanding of our own place in the cosmos. These objects remind us that our solar system is just one small part of a vast, interconnected universe filled with countless star systems, each with its own unique history and composition. They challenge us to think bigger, to see beyond the boundaries of our own cosmic neighborhood and explore the broader tapestry of the universe. This quest to uncover interstellar relics is more than just a scientific endeavor, it's a journey of discovery, one that connects us to the stars in ways we're only beginning to understand. Every object we detect, every mission we plan, brings us closer to unraveling the mysteries of the cosmos. And as we continue to explore, we're reminded that the universe is full of surprises, waiting to be uncovered by those who dare to look. The search for interstellar relics isn't just about finding objects, it's about finding ourselves in the grand story of the universe. Imagine a star so ancient that it has witnessed nearly the entire history of the universe, a celestial elder that glows with the faint light of a time long before galaxies, planets, or even the elements essential for life existed. These are the oldest stars in the cosmos, cosmic relics that carry the chemical fingerprints of the universe's infancy. Born in the chaotic aftermath of the Big Bang, these ancient luminaries are more than just astronomical curiosities. They're time capsules, offering us a rare glimpse into a universe that was vastly different from the one we know today. The story of these primordial stars begins nearly 14 billion years ago, just a few 100 million years after the Big Bang. In this early era, the universe was a simpler place, composed almost entirely of hydrogen and helium, the lightest and most basic elements. There were no heavy elements like carbon, oxygen, or iron, no planets and no life. The first stars, often referred to as population Roman 3 stars, formed from these pristine gases, igniting the cosmos with their brilliant light. While these earliest stars are long gone, their descendant stars that formed shortly afterward still shine today, preserving the chemical makeup of that primordial era. One of the most famous of these ancient stars is HD 140,283, often called the Methuselah star. Located over 200 light-years from Earth, this star is estimated to be around 13.5 billion years old, making it one of the oldest known objects in the universe. Its age is so close to that of the universe itself that it sparked a scientific debate when initial estimates suggested it might even predate the Big Bang, a paradox later resolved by refining measurement techniques. What makes Methuselah so special isn't just its age, but its composition. Unlike younger stars, which contain traces of heavier elements forged in supernova, Methuselah is almost entirely hydrogen and helium, a relic from a time before the universe was enriched with heavier elements. Identifying and studying these ancient stars is no small feat. Astronomers rely on a technique called spectroscopy, which analyzes the light emitted by stars to determine their chemical composition. By studying the specific wavelengths of light absorbed by a star's atmosphere, scientists can identify the elements present and measure their abundance. Stars like Methuselah stand out because their spectra show extremely low levels of metals, a term astronomers use to describe all elements heavier than hydrogen and helium. This metal-poor signature is a telltale marker of stars that formed in the universe's earliest days, before successive generations of stars had time to enrich the cosmos with heavier elements. But how do we determine the age of these stars? One method involves measuring their distances and motions to calculate their positions in the universe's timeline. Another approach looks at their brightness and temperature, which can reveal clues about their life cycles. For Methuselah, precise measurements of its distance and luminosity, combined with its metal-poor composition, allowed astronomers to estimate its age with remarkable accuracy. These techniques not only help us date ancient stars, but also provide insights into the conditions of the early universe, painting a picture of a time when galaxies were just beginning to take shape. The implications of studying these ancient stars extend far beyond their age and composition. They offer a window into the processes that shaped the universe in its infancy, from the formation of the first stars to the creation of the elements that make up everything we see around us. By studying stars like Methuselah, we're piecing together the story of how the universe evolved from a sea of simple gases to the complex, diverse cosmos we inhabit today. These stars remind us that the universe has a history, one that's written in the light of its oldest inhabitants. As we continue to explore these cosmic relics, we're not just uncovering the past, we're also gaining a deeper understanding of the forces that shaped our universe. These ancient stars are more than just remnants of a bygone era. They're living records of the cosmos' earliest days, offering us a chance to connect with a universe that existed long before our own. And as we look to the future, they remind us that the story of the universe is still being written, with countless mysteries waiting to be uncovered in the light of the stars. Among the countless stars that dot the night sky, one stands out as a true cosmic elder, a living fossil from the dawn of time. Known as HD 140,283, or more commonly, the Methuselah star, this ancient luminary has witnessed nearly the entire history of the universe. Its light, traveling over 200 light-years to reach us, carries the story of a time when the cosmos was young and galaxies were just beginning to form. But what makes this star so extraordinary isn't just its age. It's the secrets it holds about the universe's earliest days. The Methuselah star was first discovered in the early 20th century, but its true significance wasn't understood until much later. Early observations revealed it to be a relatively nearby star, but its faint glow and unusual composition set it apart. Unlike most stars, which contain traces of heavier elements like carbon and iron, Methuselah is almost entirely made up of hydrogen and helium, the simplest and oldest elements in the universe. This metal-poor composition hinted at its ancient origins, but pinpointing its exact age proved to be a challenge. Initial estimates suggested it might even predate the Big Bang itself, a paradox that sent scientists back to the drawing board to refine their calculations. Determining the age of a star like Methuselah is no simple task. Astronomers rely on a combination of techniques, from measuring its brightness and temperature to analyzing its motion through space. By studying its position and trajectory, they can trace its origins back to the early universe. Additionally, spectroscopy, a method that breaks down the light from a star into its component wavelengths, reveals its chemical makeup. The lack of heavy elements in Methuselah's spectrum provided a crucial clue. This star formed before successive generations of stars had enriched the cosmos with heavier elements. It's a relic from a time when the universe was still in its infancy, a snapshot of a simpler, more primordial era. What makes Methuselah so valuable to astronomers isn't just its age, but what it tells us about the early universe. Its composition reflects the conditions of the cosmos shortly after the Big Bang, when the only elements present were hydrogen, helium, and trace amounts of lithium. By studying stars like Methuselah, scientists can piece together how the first stars formed and how they seeded the universe with the heavier elements that would eventually give rise to planets, life, and everything we see around us today. This star is like a time capsule, preserving the chemical fingerprints of a universe that no longer exists. But the Methuselah star isn't just a window into the past, it's also reshaping our understanding of stellar evolution. Its existence challenges some of our assumptions about how stars form and age. For instance, its extreme age suggests that some stars may have formed earlier than previously thought, pushing back the timeline of the universe's first stellar generations. This has profound implications for our models of cosmic history, forcing us to reconsider how quickly the early universe transitioned from a dark, featureless void to a vibrant, star-filled cosmos. The search for ancient stars like Methuselah is far from over. Astronomers are now combing the skies for other metal-poor stars, hoping to find more relics from the universe's infancy. Each discovery adds another piece to the puzzle, helping us refine our understanding of how the cosmos evolved. These stars aren't just scientific curiosities, they're the keys to unlocking the story of our universe from its fiery birth to the complex, diverse cosmos we inhabit today. As we continue to study stars like Methuselah, we're reminded of the incredible scale of cosmic time. This star has been shining since before the Earth, the Sun, or even the Milky Way existed. Its light connects us to a universe that is both ancient and ever-changing, a place where the past and present are intertwined in ways we're only beginning to understand. And as we look to the future, these ancient stars remind us that the story of the universe is still being written, with countless mysteries waiting to be uncovered in the light of the stars. Imagine being able to peer back in time to the very first moments of the universe, to witness the fiery birth of everything we know. While we can't travel back billions of years, we do have the next best thing, a faint glow that permeates the cosmos, carrying the echoes of that explosive beginning. This glow, known as the cosmic microwave background, or CMB, is the oldest light in the universe, a relic from the Big Bang itself. It's not just a whisper from the past, it's a detailed snapshot of the universe when it was just 380,000 years old, a time before stars, galaxies, or even atoms as we know them existed. The story of the CMB begins with the Big Bang, the event that set the universe in motion. In its earliest moments, the cosmos was a seething, opaque soup of particles and energy, so dense and hot that light couldn't travel freely. But as the universe expanded and cooled, it reached a critical point where protons and electrons combined to form neutral hydrogen atoms. This process, called recombination, allowed photons, particles of light, to travel freely for the first time. These photons, released in that ancient moment, have been traveling through space ever since, stretched and cooled by the expansion of the universe into the faint microwave radiation we detect today. The discovery of the CMB in 1965 was a watershed moment in cosmology. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a sensitive antenna at Bell Labs when they stumbled upon a persistent noise that seemed to come from every direction in the sky. At first, they thought it was interference, perhaps from pigeon droppings on their equipment. But after meticulous testing, they realized they had found something far more profound: the afterglow of the Big Bang. This discovery not only confirmed the Big Bang theory, but also provided the first direct evidence of the universe's explosive origin. What makes the CMB so remarkable is the wealth of information it contains. Tiny fluctuations in its temperature variations of just a few millionths of a degree reveal the seeds of cosmic structure. These minuscule ripples are the imprints of density fluctuations in the early universe, regions where matter was slightly more or less dense than average. Over billions of years, these fluctuations grew under the influence of gravity, eventually giving rise to the galaxies, stars, and planets we see today. In a sense, the CMB is a cosmic blueprint, showing us the initial conditions from which the entire universe evolved. But the CMB isn't just a relic of the past, it's also a powerful tool for understanding the present and future of the cosmos. By studying its properties, scientists can measure the universe's rate of expansion, determine its age, and even probe the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Missions like NASA WMAP and the European Space Agency's Planck have mapped the CMB with unprecedented precision, revealing subtle details about the universe's composition and evolution. These observations have helped refine our understanding of cosmology, confirming key predictions of the Big Bang theory while also raising new questions. One of the most intriguing aspects of the CMB is what it tells us about the universe's origins. The patterns we see in the microwave background are consistent with the idea of cosmic inflation, a rapid expansion of the universe in the first fraction of a second after the Big Bang. This theory suggests that the universe underwent an exponential growth spurt, smoothing out irregularities and setting the stage for the large-scale structure we observe today. While inflation remains a theoretical framework, the CMB provides some of the strongest evidence supporting it, offering a glimpse into the earliest moments of cosmic history. The study of the CMB is far from over. As technology advances, scientists are developing new ways to analyze this ancient light, searching for clues about the universe's earliest moments. Future missions aim to detect even fainter signals hidden within the CMB, such as the imprint of gravitational waves from the inflationary epoch. These discoveries could revolutionize our understanding of the Big Bang and shed light on the fundamental forces that shape the cosmos. The cosmic microwave background is more than just a relic of the Big Bang. It's a bridge connecting us to the universe's origins. By studying this ancient light, we're not just exploring the past, we're uncovering the story of how the universe grew from a hot, dense state into the vast, complex cosmos we inhabit today. It's a reminder that the universe has a history, one that's written in the faint glow of its oldest light. And as we continue to decode its secrets, we're taking a step closer to understanding not just where we came from, but how we fit into the grand tapestry of the cosmos. The Planck mission, launched by the European Space Agency in 2009, was designed to do something extraordinary: capture the most detailed map of the cosmic microwave background ever created. Think of it as a cosmic time machine peering back over 13 billion years to the universe's infancy. This mission wasn't just about taking a snapshot of ancient light. It was about decoding the secrets hidden within that light, secrets that could rewrite our understanding of the cosmos. And what it revealed has reshaped cosmology in ways we're still unraveling. At its core, Planck's goal was to measure the tiny temperature fluctuations in the CMB, those faint ripples left over from the Big Bang. These fluctuations, no larger than a few millionths of a degree, are like cosmic fingerprints, encoding information about the universe's age, composition, and evolution. To achieve this, Planck was equipped with some of the most sensitive instruments ever built, capable of detecting even the subtlest variations in the microwave background. Over 4 years, it scanned the entire sky, gathering data with unparalleled precision. The result, the most detailed map of the early universe ever created, a masterpiece of cosmic cartography. One of Planck's most groundbreaking discoveries was a precise measurement of the universe's age, 13.8 billion years, give or take a few million. This figure, refined from earlier estimates, has become the gold standard for cosmology, anchoring our understanding of cosmic history. But Planck didn't stop there. It also revealed the universe's composition with remarkable accuracy, showing that ordinary matter, the stuff of stars, planets, and people, makes up just under 5% of the cosmos. The rest, dark matter and dark energy, two mysterious components that dominate the universe but remain largely unexplained. These findings have profound implications, not just for cosmology, but for our understanding of the fundamental forces shaping the cosmos. Perhaps the most tantalizing aspect of Planck's data is what it tells us about cosmic inflation, the theory that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. The patterns in the CMB align closely with predictions made by inflation models, providing some of the strongest evidence yet for this theory. Planck's observations also revealed subtle anomalies in the CMB, hints that our understanding of inflation and perhaps the Big Bang itself might need refinement. These anomalies have sparked intense debate among scientists, driving new research and pushing the boundaries of our knowledge. The legacy of the Planck mission extends far beyond its data. It has set the stage for future missions like the upcoming James Webb Space Telescope and planned CMB observatories, which aim to probe even deeper into the universe's origins. These missions will build on Planck's foundation, searching for clues about the nature of dark energy, the properties of neutrinos, and the possibility of other universes beyond our own. In a sense, Planck has opened a door to a new era of cosmology, one where the questions are as exciting as the answers. What makes Planck so extraordinary isn't just the precision of its measurements, it's the way it connects us to the universe's beginnings. By mapping the CMB, Planck has given us a glimpse of the cosmos in its infancy, a time when the universe was a hot, dense soup of particles and energy. It's a reminder that the story of the universe is also our story, written in the faint glow of ancient light. And as we continue to explore this cosmic relic, we're not just uncovering the past, we're charting the future of our understanding of the cosmos. The Planck mission is a testament to humanity's curiosity and ingenuity, a reminder that even the faintest whispers from the universe can reveal profound truths. As we turn our gaze to the stars, we're reminded that the universe is full of mysteries waiting to be uncovered, and that every discovery brings us closer to understanding where we came from and where we might be headed. Let's take a journey back to the universe's infancy, a time when the cosmos was a seething cauldron of energy and matter. In this chaotic environment, something extraordinary might have formed primordial black holes. Unlike the black holes we know today, which are born from the collapse of massive stars, these hypothetical objects could have emerged in the earliest moments after the Big Bang. Imagine a black hole not forged by a dying star, but by the extreme density and temperature fluctuations of the early universe itself. These relics, if they exist, could hold the key to some of the universe's greatest mysteries, from the nature of dark matter to the formation of galaxies. The theory behind primordial black holes is both elegant and intriguing. In the first fractions of a second after the Big Bang, the universe was a rapidly expanding, incredibly dense soup of energy and matter. Tiny irregularities in this primordial soup, fluctuations in density, could have caused some regions to collapse under their own gravity, forming black holes. These objects would have been incredibly small, perhaps no larger than an atom, yet they could have packed the mass of a mountain. Over billions of years, some of these primordial black holes might have grown, either by merging with others or by gobbling up surrounding matter, becoming the supermassive black holes we observe at the centers of galaxies today. Detecting these ancient objects, however, is no easy task. Unlike stellar black holes, which are often surrounded by swirling disks of gas and dust, primordial black holes are thought to be isolated and nearly invisible. Their small size and lack of interaction with light make them incredibly elusive. Scientists have proposed a few methods to find them, such as looking for the gravitational effects they might have on light from distant stars, a phenomenon known as microlensing. Another approach involves searching for the telltale bursts of radiation that could occur if a primordial black hole collided with a neutron star or another black hole. But so far, these efforts have yet to yield definitive evidence, leaving primordial black holes in the realm of tantalizing possibility. One of the most exciting implications of primordial black holes is their potential connection to dark matter. This mysterious substance, which makes up about 27% of the universe, doesn't emit, absorb, or reflect light, making it invisible to our telescopes. While dark matter is often thought to be composed of exotic particles, some scientists have proposed that primordial black holes could account for at least a portion of it. If true, this would solve one of cosmology's biggest puzzles, providing a natural explanation for dark matter's gravitational effects without the need for new particles. It's a bold idea and one that continues to spark debate and inspire research. Beyond dark matter, primordial black holes could also shed light on how galaxies formed. The early universe was a relatively smooth place with matter distributed almost evenly, but over time, gravity caused this matter to clump together, forming the first stars and galaxies. If primordial black holes existed, their immense gravity could have acted as cosmic seeds, accelerating the process of galaxy formation. This would explain why we see such massive structures in the universe today, from galaxy clusters to supermassive black holes at the hearts of galaxies. In a sense, primordial black holes could be the architects of the cosmos, shaping the universe on the grandest scales. The search for primordial black holes is more than just a scientific curiosity. It's a quest to understand the universe's earliest moments. By studying these elusive objects, we're not just exploring the nature of black holes, we're uncovering the story of how the cosmos evolved from a hot, dense state into the vast, complex web of galaxies we see today. Every observation, every theory brings us closer to answering some of the most profound questions in science. What is dark matter? How did galaxies form? And what role did the universe's earliest structures play in shaping the cosmos as we know it? As we continue to probe the mysteries of primordial black holes, we're reminded that the universe is full of surprises. These ancient relics born in the chaos of the Big Bang could hold the answers to questions we've only just begun to ask. And as we look to the stars, we're not just searching for black holes, we're searching for the story of the universe itself, written in the faint whispers of its earliest days. Imagine a universe where most of the matter is invisible, not just hidden, but fundamentally undetectable by the light we see. This isn't science fiction. It's the reality of dark matter, a mysterious substance that makes up roughly 27% of the universe's total mass and energy. Unlike stars, planets, or even black holes, dark matter doesn't emit, absorb, or reflect light. It's completely transparent, yet its gravitational influence is undeniable. From the way galaxies rotate to the way clusters of galaxies move, dark matter's fingerprints are everywhere, shaping the cosmos in ways we're only beginning to understand. The story of dark matter begins with a puzzle. In the 1930s, Swiss astronomer Fritz Zwicky noticed something strange about the Coma cluster, a massive collection of galaxies. Based on the visible matter he observed, the cluster's gravity shouldn't have been strong enough to hold its galaxies together. Yet they were moving far faster than expected, as if held by an invisible force. Zwicky called this unseen mass dark matter, a term that has since become central to our understanding of the universe. Decades later, astronomer Vera Rubin found similar evidence in spiral galaxies, where stars on the outer edges were orbiting far too quickly to be explained by the visible matter alone. Together, these observations painted a startling picture. The universe is filled with something we can't see, but whose gravity shapes everything we can. So, what exactly is dark matter? While we don't yet know its true nature, scientists have proposed several candidates. One leading theory suggests that dark matter is made up of weakly interacting massive particles, or WIMP. These hypothetical particles are thought to interact only through gravity and possibly the weak nuclear force, making them incredibly difficult to detect. Imagine trying to spot a ghost that passes through walls without leaving a trace. That's the challenge of hunting for WIMP. Despite their elusiveness, WIMP remain a prime focus of dark matter research, with experiments around the world designed to capture even the faintest signals of their existence. Detecting dark matter is no small feat. One approach involves placing ultra-sensitive detectors deep underground, shielded from cosmic rays and other interference. These experiments, like the Large Underground Xenon Lux Detector, search for the rare occasions when a WIMP might collide with a normal atom, producing a tiny flash of light or heat. Another method looks for indirect evidence, such as gamma rays or other particles that could be produced when dark matter particles annihilate each other in space. While these experiments have yet to yield a definitive detection, they've narrowed down the possibilities, bringing us closer to solving one of the greatest mysteries in science. The implications of discovering dark matter go far beyond identifying a new particle. This elusive substance plays a crucial role in the universe's structure and evolution. Without dark matter's gravitational pull, galaxies wouldn't have formed as they did, and the cosmic web, the vast network of filaments and voids that define the universe's large-scale structure, wouldn't exist. In a sense, dark matter is the scaffolding of the cosmos, the unseen framework upon which everything else is built. Understanding it could unlock new insights into how galaxies form, how the universe evolved, and even the fate of the cosmos itself. But dark matter isn't just a scientific curiosity, it's a reminder of how much we still have to learn about the universe. Its existence challenges us to rethink our assumptions, to explore new ideas, and to push the boundaries of what we thought was possible. The search for dark matter is more than just a quest to uncover a hidden particle. It's a journey to understand the invisible forces that shape our reality. And as we continue to explore this cosmic mystery, we're reminded that the universe is full of surprises, waiting to be uncovered by those who dare to look beyond the light. This quest to uncover dark matter is part of a broader effort to understand the universe's hidden components. From dark energy, which drives the accelerated expansion of the cosmos, to the mysterious particles that might make up dark matter, these invisible forces are reshaping our understanding of reality. Together, they form a cosmic puzzle, one that challenges us to think bigger, to explore deeper, and to see the universe not as a static collection of stars and galaxies, but as a dynamic, ever-changing system. As we continue to probe these mysteries, we're not just uncovering the secrets of the cosmos, we're redefining our place within it. As we journey further back in time, beyond the formation of stars and the birth of the first atoms, we arrive at a pivotal moment in the universe's history, the cosmic dawn. This era, just a few 100 million years after the Big Bang, marks the birth of the first galaxies, the earliest structures to emerge in a universe that was once nothing but a sea of darkness. These ancient galaxies are more than just relics of the past. They're the cornerstones of cosmic evolution, offering us a glimpse into how the universe transformed from a featureless expanse into the vibrant, structured cosmos we see today. The first galaxies didn't form overnight. In the aftermath of the Big Bang, the universe was a chaotic, swirling mass of gas, mostly hydrogen and helium, with tiny ripples of density scattered throughout. Over millions of years, gravity began to pull these ripples together, creating denser regions where gas clouds could collapse and ignite the first stars. These early stars, burning brightly and briefly, gathered into small clusters which eventually merged to form the first galaxies. These primordial structures were the seeds of everything to come, the building blocks of the vast cosmic web we now observe. Observing these ancient galaxies, however, is no easy task. The light from these distant objects has traveled for billions of years to reach us, stretched and dimmed by the expansion of the universe. What was once visible light has been redshifted into the infrared, making it nearly invisible to traditional telescopes. To detect these faint whispers from the cosmic dawn, astronomers rely on cutting-edge technology like the Hubble Space Telescope and its successor, the James Webb Space Telescope. These instruments are equipped with sensitive infrared detectors, allowing them to peer through the cosmic haze and capture the faint glow of the universe's earliest galaxies. One of the most remarkable discoveries in this field is the galaxy GNZ11, detected by Hubble in 2016. Located over 13.4 billion light-years away, GNZ11 is one of the oldest and most distant galaxies ever observed. Its light offers a snapshot of the universe when it was just 400 million years old, a time when galaxies were in their infancy. GNZ11 is small compared to modern galaxies, but it's incredibly bright, suggesting that it formed stars at an astonishing rate. This discovery has challenged our understanding of galaxy formation, showing that even in the universe's earliest days, galaxies could grow and evolve much faster than we once thought. But GNZ11 is just the beginning. As telescopes like James Webb come online, they're expected to reveal even more galaxies from this era, painting a clearer picture of the cosmic dawn. These observations will help us understand how galaxies formed and evolved, shedding light on the processes that shape the universe's large-scale structure. For example, did galaxies form gradually through the slow accumulation of gas and stars, or did they burst onto the scene, forming rapidly in a flurry of star formation? The answers to these questions could revolutionize our understanding of cosmic history. The study of these ancient galaxies isn't just about uncovering the past, it's also about understanding the present. The first galaxies laid the groundwork for everything that followed, from the formation of supermassive black holes to the birth of complex structures like galaxy clusters. By studying them, we're tracing the origins of the cosmic web, the intricate network of filaments and voids that defines the universe's structure. These early galaxies are like the first threads in a cosmic tapestry, weaving together the story of how the universe grew from simplicity to complexity. What's truly awe-inspiring is how these discoveries connect us to the cosmos. The light from galaxies like GNZ11 has traveled for billions of years to reach us, carrying with it the story of the universe's earliest days. By studying these ancient relics, we're not just exploring distant galaxies, we're uncovering the roots of our own cosmic home. And as we continue to probe the depths of space, we're reminded that the universe is full of mysteries, waiting to be uncovered by those who dare to look beyond the stars. The first galaxies are more than just relics of the cosmic dawn. They're a testament to the universe's capacity for growth and transformation. From the faintest flickers of light to the sprawling galactic cities we see today, these ancient structures remind us that the cosmos is a dynamic, ever-changing place. And as we continue to explore their secrets, we're not just uncovering the past, we're charting the future of our understanding of the universe. Imagine looking through a cosmic telescope and catching a glimpse of a galaxy so far away that its light has traveled over 13 billion years to reach us. This isn't just a galaxy, it's a time capsule, a window into a universe that was just 400 million years old. Meet GNZ11, one of the most distant and ancient galaxies ever discovered. Its light, stretched and redshifted by the expansion of the universe, carries the story of a time when galaxies were in their infancy, and the cosmos was still taking its first steps toward the complexity we see today. GNZ11 isn't just a scientific curiosity, it's a key to unlocking the secrets of the early universe. The discovery of GNZ11 in 2016 by the Hubble Space Telescope was a landmark moment in astronomy. Located in the constellation Ursa Major, this faint smudge of light holds the distinction of being the most distant galaxy ever observed, with a redshift of 11.1. Redshift, a measure of how much the light from an object has been stretched by the expansion of the universe, is a crucial tool for astronomers. The higher the redshift, the farther away and the older the object is. For GNZ11, this extreme redshift places it at the very edge of our observable universe, offering a rare glimpse into the cosmic dawn. What makes GNZ11 so special isn't just its distance, but the insights it provides into the early stages of galaxy formation. Despite its age, this ancient galaxy is surprisingly bright, suggesting it was forming stars at a prodigious rate. In fact, GNZ 11 is churning out new stars 20 times faster than our own Milky Way, a remarkable feat for a galaxy so young. This challenges our understanding of how galaxies grow and evolve, showing that even in the universe's earliest days, some galaxies were already thriving and dynamic. It's like finding a toddler who's already a chess prodigy, an anomaly that forces us to rethink our assumptions. Studying GNZ 11 has also shed light on the conditions of the early universe. The light from this ancient galaxy reveals that it contains heavy elements like carbon and oxygen, which are forged in the hearts of stars and scattered through supernova. This suggests that GNZ 11 had already experienced multiple generations of star formation and death, a process that would have taken hundreds of millions of years. In other words, this galaxy was already mature by the time its light began its journey to us, hinting at a universe that was far more active and complex in its youth than we once thought. The implications of GNZ 11's discovery extend far beyond this single galaxy. It provides a crucial data point in our understanding of how galaxies form and evolve, helping us piece together the timeline of cosmic history. By studying galaxies like GNZ 11, astronomers can test theories about the growth of cosmic structures, the role of dark matter, and the interplay between stars, gas, and dust in the early universe. Each observation brings us closer to answering fundamental questions. How did the first galaxies form? What drove their rapid growth? And how did they shape the universe we see today? But GNZ 11 is just the beginning. As next-generation telescopes like the James Webb Space Telescope come online, they're expected to reveal even more ancient galaxies, pushing the boundaries of our cosmic horizon. These discoveries will allow us to map the universe's infancy in unprecedented detail, tracing the first steps of galaxy formation and the emergence of the cosmic web. In a sense, GNZ 11 is like the first chapter in a cosmic history book, a tantalizing glimpse of what's to come as we continue to explore the universe's origins. The story of GNZ 11 reminds us that the universe is full of surprises, waiting to be uncovered by those who dare to look deeper. This ancient galaxy, born in the fires of the cosmic dawn, connects us to a time long before Earth, the Sun, or even the Milky Way existed. As we continue to study it and others like it, we're not just uncovering the past, we're charting the future of our understanding of the cosmos. And with each new discovery, we're reminded that the universe is a dynamic, ever-changing place filled with stories waiting to be told. Enter the James Webb Space Telescope, or JWST, a marvel of modern engineering and humanity's most ambitious window into the cosmos. Launched in December 2021, JWST isn't just another telescope, it's a revolutionary tool designed to peer deeper into space and further back in time than ever before. With its massive golden mirror and state-of-the-art infrared instruments, this telescope is poised to transform our understanding of the universe's earliest moments, shedding light on cosmic relics that have remained hidden for billions of years. From the birth of the first galaxies to the atmospheres of distant exoplanets, JWST is unlocking secrets that were once beyond our reach. What sets JWST apart is its ability to observe in infrared light, a part of the spectrum invisible to the human eye. This capability is crucial for studying the universe's ancient relics, as the light from the earliest galaxies has been stretched into the infrared by the expansion of the universe. Traditional telescopes like Hubble, while groundbreaking, are limited in their ability to detect this redshifted light. JWST, on the other hand, is specifically designed to capture these faint signals, allowing us to see farther back in time and closer to the Big Bang than ever before. It's like swapping a candle for a spotlight, illuminating the darkest corners of the cosmos. One of JWST's primary goals is to study the first galaxies that formed in the universe, objects like GNZ 11, but even older and more distant. By capturing the light from these ancient structures, the telescope can help us answer fundamental questions about how galaxies form and evolve. Did galaxies grow slowly, accumulating stars and gas over billions of years? Or did they burst onto the scene in a flurry of star formation, as some early observations suggest? JWST's unprecedented resolution and sensitivity are already providing new insights, revealing galaxies that existed just a few 100 million years after the Big Bang, a time when the universe was still in its infancy. But JWST isn't just looking back in time, it's also exploring the present and future of the cosmos. Among its many targets are exoplanets, worlds orbiting distant stars. Using a technique called transit spectroscopy, JWST can analyze the atmospheres of these planets, searching for chemical signatures that might indicate the presence of water, methane, or even signs of life. This capability is particularly exciting for studying Earth-like planets in the habitable zones of their stars, where conditions might be right for liquid water and potentially life as we know it. Imagine the moment when JWST detects a planet with an atmosphere rich in oxygen or other biomarkers. It could be the first hint of life beyond Earth. The implications of JWST discoveries extend far beyond individual galaxies or planets. By studying the universe's earliest structures, the telescope is helping us piece together the story of how the cosmos evolved from a hot, dense state into the complex web of galaxies, stars, and planets we see today. It's also probing the nature of dark matter and dark energy, the mysterious forces that shape the universe's large-scale structure. Every image, every spectrum, and every dataset from JWST adds another piece to the cosmic puzzle, bringing us closer to understanding the universe's origins and its ultimate fate. Looking ahead, JWST is just the beginning. Its discoveries will pave the way for future missions, both on the ground and in space, that will build on its legacy. From next-generation telescopes to ambitious space observatories, the tools we develop in the coming decades will continue to push the boundaries of what we know about the universe. JWST is not just a telescope, it's a beacon of human curiosity and ingenuity, reminding us that the cosmos is full of wonders waiting to be uncovered. As we continue to explore the universe with JWST, we're not just uncovering ancient relics, we're rediscovering our own place in the cosmos. Every galaxy, every exoplanet, and every new discovery connects us to the vast, interconnected story of the universe. And with each revelation, we're reminded that the journey to understand the cosmos is as much about the questions we ask as the answers we find. The James Webb Space Telescope is more than a tool. It's a testament to humanity's unending quest to explore the unknown and uncover the secrets of the stars. As we stand on the cusp of a new era in cosmic exploration, the future of uncovering relics from the universe's past has never looked brighter. With cutting-edge missions and groundbreaking technologies on the horizon, we're poised to unlock mysteries that have remained hidden for billions of years. From interstellar objects zipping through our solar system to ancient stars that glow with the light of the early universe, the next chapter in cosmic discovery promises to redefine our understanding of the cosmos and our place within it. One of the most exciting developments is the next generation of space telescopes, like the James Webb Space Telescope and its successors. These instruments are designed to peer deeper into space and further back in time than ever before, capturing the faint light of galaxies born just after the Big Bang. But the future doesn't stop there. Missions like the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will map the cosmos in unprecedented detail, searching for clues about dark energy and the universe's expansion. These telescopes are more than just tools, they're time machines allowing us to witness the universe's earliest moments and trace its evolution to the present day. On the ground, observatories like the Vera C. Rubin Observatory in Chile are set to revolutionize our ability to detect fleeting cosmic phenomena. With its massive camera capable of capturing the entire visible sky every few nights, Rubin will scan the heavens for interstellar visitors, ancient stars, and even the faint signals of dark matter. This relentless survey of the night sky will provide a treasure trove of data, offering new insights into the objects that shaped our universe and the forces that continue to drive its evolution. But the future of cosmic relic discovery isn't just about technology, it's also about collaboration. Across the globe, scientists from different nations and disciplines are coming together to tackle the universe's greatest mysteries. Projects like the Event Horizon Telescope, which captured the first image of a black hole, are shining examples of what humanity can achieve when we work together. These partnerships are essential for tackling complex challenges, from decoding the nature of dark matter to tracking the origins of interstellar objects. In a world often divided, the shared pursuit of cosmic knowledge reminds us of our common curiosity and the boundless potential of collective effort. What makes this era of discovery so thrilling is the sheer potential for groundbreaking finds. Imagine uncovering new interstellar objects, each carrying clues about the conditions in distant star systems. Or detecting ancient stars that formed before the Milky Way, offering a glimpse into the universe's earliest days. Perhaps most tantalizing is the possibility of identifying dark matter particles, the elusive substance that makes up most of the universe's mass. Each of these discoveries would not only deepen our understanding of the cosmos, but also challenge us to rethink our place within it. The implications of these future discoveries extend far beyond science. They remind us that the universe is a vast, interconnected system, shaped by forces we're only beginning to understand. As we uncover more about the universe's origins and evolution, we're also uncovering more about ourselves. The story of the cosmos is in many ways our story, a tale of curiosity, exploration, and the unending quest to understand the world around us. Looking ahead, the future of cosmic relic discovery is not just about finding answers, it's about asking better questions. With each new mission, each new telescope, and each new collaboration, we're pushing the boundaries of what we know and venturing into uncharted territory. The universe is full of surprises, and as we continue to explore, we're reminded that the journey is just as important as the destination. The stars have always called to us, and now, more than ever, we're ready to answer. As we marvel at the ancient wonders of the cosmos, stardust older than our solar system, meteorites that may have carried life's building blocks, and galaxies born in the universe's infancy, it's worth pausing to ask, what responsibilities come with studying these cosmic relics? Beyond the scientific breakthroughs and awe-inspiring discoveries, there's an ethical dimension to this exploration that deserves our attention. How do we ensure that our quest for knowledge doesn't come at the cost of preserving these ancient treasures or disrupting the delicate balance of the cosmos? These questions aren't just philosophical, they're practical, shaping how we approach space exploration and the study of the universe's oldest artifacts. One of the most pressing ethical considerations is the preservation of these cosmic relics. When a meteorite falls to Earth or a spacecraft collects samples from an asteroid, we're handling materials that have existed for billions of years, far longer than human civilization itself. These objects are not just scientific specimens, they're time capsules carrying the story of the universe's origins. Removing them from their natural environment or altering them during study risks losing invaluable information. For example, some meteorites contain organic compounds that could degrade if exposed to Earth's atmosphere or mishandled in a lab. Responsible scientific practices, such as non-destructive testing and careful storage, are essential to ensure these relics remain intact for future generations to study. At the same time, space exploration itself raises ethical questions. Missions to asteroids, comets, and even distant planets have the potential to uncover groundbreaking insights, but they also carry the risk of contaminating these pristine environments. Imagine a spacecraft landing on Mars, inadvertently introducing Earth-based microbes to the red planet's surface. Such contamination could not only compromise scientific findings, but also disrupt any potential ecosystems that might exist. This is why space agencies like NASA and ESA adhere to strict planetary protection protocols, ensuring that exploration is conducted with minimal impact on the environments we study. Another layer of ethical consideration is the role of international cooperation in the study of cosmic relics. Space exploration is no longer the domain of a few nations. It's a global endeavor, with countries and private companies collaborating on missions that span the solar system. This shared effort brings incredible opportunities, but it also requires a commitment to fairness and transparency. Who owns the materials collected from asteroids or the data gathered from distant galaxies? How do we ensure that the benefits of space exploration are shared equitably rather than monopolized by a few? These questions highlight the need for international agreements and ethical frameworks that guide how we explore and utilize the cosmos. Beyond the practical and legal considerations, there's also a deeper, more philosophical dimension to studying cosmic relics. These ancient artifacts remind us of our place in the universe, not as its masters, but as its students. They inspire awe and curiosity, connecting us to a story that began long before Earth existed and will continue long after we're gone. This perspective fosters humility, encouraging us to approach the cosmos with respect and reverence. It's a reminder that science isn't just about discovery. It's about stewardship, ensuring that we leave the universe as we found it for future generations to explore. The ethical implications of studying cosmic relics extend far beyond the confines of science. They challenge us to think about how we interact with the universe and with each other. They remind us that the pursuit of knowledge isn't just a technical endeavor. It's a moral one shaped by our values and our vision for the future. By embracing responsible scientific practices, fostering international cooperation, and approaching the cosmos with humility, we can ensure that our exploration of the universe is not only groundbreaking but also ethical and inclusive. As we continue to uncover the secrets of the cosmos, these ethical considerations will play an increasingly important role in shaping our journey. They remind us that the universe isn't just a place to explore. It's a shared heritage, a treasure trove of stories waiting to be uncovered. And as we reach for the stars, we're not just seeking answers, we're forging a path that reflects our highest ideals and our deepest respect for the mysteries of the cosmos. From the tiniest grains of stardust to the faint glow of the cosmic microwave background, cosmic relics are more than just ancient artifacts, they're windows into the universe's grand story. These remnants of the cosmos' earliest days have a unique power. They ignite our curiosity, pushing us to ask questions, seek answers, and imagine what lies beyond the limits of our understanding. It's this relentless drive to explore the unknown that defines us as a species, and cosmic relics are the sparks that keep that fire burning. They remind us that the universe isn't just out there, it's within us, woven into the fabric of our very existence. Take stardust, for example. These microscopic grains, older than our solar system, are tangible links to the universe's infancy. When we study them, we're not just analyzing ancient materials, we're connecting with the stars that forged them billions of years ago. It's a humbling thought. The same atoms that once burned in the hearts of ancient stars now make up the world around us and even us. This connection isn't just scientific, it's deeply personal. It reminds us that we're part of something far bigger than ourselves, a cosmic tapestry that stretches across time and space. But cosmic relics do more than connect us to the past. They inspire us to look to the future. Every meteorite that lands on Earth, every ancient galaxy we observe, and every interstellar object that passes through our solar system fuels our desire to explore. They challenge us to think bigger, to dream of what lies beyond our planet and our solar system. They remind us that the universe is full of mysteries waiting to be uncovered, and that humanity's journey of discovery is far from over. This sense of wonder isn't just the domain of scientists. It's something that resonates with people of all ages and backgrounds, sparking curiosity and imagination in ways that transcend borders and cultures. Public engagement plays a crucial role in keeping this sense of wonder alive. When we share the stories of cosmic relics, whether through museums, documentaries, or social media, we're not just educating people about science, we're inviting them to be part of the journey. Imagine a child holding a meteorite for the first time, feeling the weight of something that traveled billions of miles to reach Earth. Or consider the awe of seeing an image from the James Webb Space Telescope, capturing light from a galaxy that existed when the universe was just a fraction of its current age. These moments are more than educational. They're transformative, inspiring the next generation of explorers, scientists, and dreamers. The importance of education and outreach can't be overstated. By making the wonders of cosmic relics accessible to everyone, we're not just sharing knowledge, we're fostering a sense of connection and responsibility. We're showing that the universe isn't just something to be studied, it's something to be cherished and protected. This shared understanding is essential as we look to the future, not just of space exploration, but of humanity itself. The more we learn about the cosmos, the more we realize how interconnected we are, not just with each other, but with the universe as a whole. Looking ahead, cosmic relics hold the key to humanity's future in space. They teach us about the processes that shaped our solar system, the conditions that allowed life to emerge, and the resources that could sustain us as we venture beyond Earth. From the water in ancient meteorites to the organic molecules in interstellar dust, these relics offer clues about how life might thrive elsewhere in the universe. They also remind us of the challenges we'll face, whether it's navigating the harsh environment of space or preserving the pristine worlds we explore. But most importantly, they remind us why we explore, not just to find answers, but to ask better questions, to push the boundaries of what's possible, and to discover our place in the cosmos. As we continue to uncover the secrets of cosmic relics, we're not just exploring the universe, we're exploring ourselves. These ancient artifacts connect us to the past, inspire us in the present, and guide us toward the future. They remind us that the universe is a place of endless wonder, filled with stories waiting to be told. And as we look to the stars, we're reminded that the journey of discovery is just beginning, a journey that belongs to all of us. Cosmic relics aren't just scientific marvels, they're cultural touchstones, woven into the fabric of human imagination for millennia. Long before we understood the true nature of stardust or meteorites, these celestial objects captivated our ancestors, sparking myths, legends, and stories that sought to explain the mysteries of the cosmos. From ancient civilizations to modern storytellers, cosmic relics have shaped how we see the universe and our place within it, bridging the gap between science and the human spirit. Take the ancient Egyptians, for instance. To them, meteorites weren't just rocks from the sky, they were gifts from the gods. The famed Benben stone, a sacred object in their mythology, is thought to have been inspired by a meteorite. This celestial connection wasn't unique to Egypt. Across cultures, from the Greeks to the Native Americans, meteorites were revered as divine symbols, embodying the power and mystery of the heavens. These ancient interpretations remind us that cosmic relics have always been more than just physical objects. they've been sources of wonder, fear, and inspiration. Fast forward to the modern era, and cosmic relics continue to ignite our imagination, now through the lens of science fiction. Think of the monolith in 2001, a space odyssey, a mysterious artifact that transforms humanity's understanding of its place in the universe. Or consider the alien meteorite in Arrival, a symbol of connection and communication across the stars. These stories, rooted in the tangible reality of cosmic relics, explore profound questions about existence, identity, and the unknown. They remind us that the universe isn't just a place to explore, it's a canvas for our deepest hopes and fears. But the cultural impact of cosmic relics goes beyond storytelling. They've also inspired artists and philosophers to grapple with the vastness of the cosmos. Painters like Vincent van Gogh captured the swirling beauty of the night sky, while sculptors and architects have drawn on the shapes and textures of meteorites to create works that evoke the timelessness of the universe. Even in music, the idea of cosmic relics has found expression, from Gustav Holst's The Planets to the ethereal sounds of modern space-themed compositions. These creations reflect humanity's enduring fascination with the cosmos, a fascination that transcends time and culture. At the heart of this cultural connection is a profound truth. Cosmic relics remind us that we're part of something much larger than ourselves. They challenge us to think beyond our individual lives, our nations, and even our planet, urging us to consider our role in the grand tapestry of the universe. This perspective has profound implications for how we see ourselves and our future. If the atoms in our bodies were forged in the hearts of ancient stars, then we're not just inhabitants of the cosmos, we're its children, born from the same materials that shaped galaxies and planets. This realization has the power to unite us. In a world often divided by borders and beliefs, cosmic relics offer a shared heritage, a reminder that we're all connected by the same cosmic story. They inspire us to look up at the night sky not just with curiosity but with a sense of belonging. As we continue to explore these ancient artifacts, we're not just uncovering the history of the universe, we're rediscovering what it means to be human. The cultural significance of cosmic relics lies in their ability to bridge the past and the future, science and art, the tangible and the intangible. They remind us that the universe isn't just a place of discovery, it's a source of inspiration, a mirror reflecting our deepest questions and dreams. And as we continue to explore these relics, we're not just uncovering the secrets of the cosmos, we're shaping the story of humanity's relationship with the stars. Cosmic relics have a way of capturing our imagination, not just in the realm of science, but in the stories we tell and the worlds we create. From blockbuster movies to immersive video games, these ancient artifacts have become powerful symbols in popular culture, shaping how we view the cosmos and our place within it. Whether it's a glowing meteorite with mysterious powers or an alien artifact that holds the key to humanity's future, these portrayals often blur the line between science and fiction, sparking curiosity and wonder in audiences around the world. Think about movies like Interstellar or Contact, where cosmic relics, whether a wormhole or an alien transmission, serve as gateways to deeper questions about existence, exploration, and our connection to the universe. These stories don't just entertain, they challenge us to think about the possibilities of life beyond Earth and the mysteries that lie waiting in the stars. Even in more fantastical settings, like the Marvel Cinematic Universe, cosmic relics like the Infinity Stones become metaphors for the immense power and fragility of the cosmos, reminding us of the responsibility that comes with discovery. Video games, too, have embraced the allure of cosmic relics. Titles like Mass Effect and No Man's Sky invite players to explore vast, uncharted galaxies, where ancient artifacts hold the secrets of long-lost civilizations. These virtual experiences allow us to step into the shoes of explorers, scientists, and adventurers, fostering a sense of connection to the real-world quest for knowledge. By blending science with storytelling, these games make complex concepts like interstellar travel or the origins of life accessible and exciting, inspiring players to learn more about the science behind the fiction. But the influence of popular culture goes beyond entertainment. It shapes how we perceive space exploration and scientific discovery, often acting as a gateway to real-world curiosity. A child who watches The Martian might dream of becoming an astronaut, while someone who plays Kerbal Space Program might develop a passion for engineering. These depictions humanize the challenges and triumphs of space exploration, making them relatable and inspiring. They remind us that science isn't just about data and equations. It's about the human spirit, the drive to explore, and the courage to ask big questions. At the same time, popular culture has the potential to simplify or sensationalize the complexities of cosmic relics and space science. While a movie might depict a meteorite as a magical object with instant answers, the reality is often far more nuanced. This is where science communication plays a crucial role. By bridging the gap between fiction and fact, educators and communicators can use these cultural touchstones as entry points to deeper discussions. For example, a film about an alien artifact could spark a conversation about the search for extraterrestrial life, or a game about interstellar exploration could lead to a lesson on the physics of space travel. The broader implications of this cultural connection are profound. When popular culture inspires interest in cosmic relics and space science, it creates a ripple effect. More people engage with science, more students pursue STEM careers, and more funding flows toward research and exploration. It's a reminder that science doesn't exist in a vacuum. It's part of our shared human experience, shaped by the stories we tell and the dreams we share. As we continue to explore the cosmos, both in reality and in our imaginations, these cultural depictions will remain a vital part of the journey. They remind us that the universe isn't just a place of discovery, it's a source of inspiration, a canvas for our hopes and fears, and a mirror reflecting our deepest questions. By embracing the stories that connect us to the stars, we're not just exploring the cosmos, we're celebrating the human spirit's unending quest to understand its place in the universe. And as we look to the future, this connection will continue to inspire, educate, and unite us in the shared adventure of discovery. While professional scientists play a vital role in uncovering the secrets of cosmic relics, they're not the only ones shaping our understanding of the universe. Enter citizen scientists, everyday individuals who contribute to groundbreaking discoveries through their passion, curiosity, and dedication. From hunting for meteorites in remote deserts to sifting through microscopic stardust, these volunteers are proving that you don't need a lab coat to make a meaningful impact on science. Their efforts not only expand the scope of research, but also remind us that the quest to understand the cosmos is a shared human endeavor. One of the most exciting ways citizen scientists contribute is through meteorite hunting. When a fireball streaks across the sky, it's often the public who first reports the event, providing crucial data about the meteor's trajectory. Networks like the American Meteor Society rely on these observations to calculate where fragments might land. Once a potential fall zone is identified, volunteers fan out across the landscape, armed with metal detectors and a keen eye for rocks that don't quite belong. Some of the most significant meteorite discoveries in recent years, like the Winchcombe meteorite in the UK, have been made by ordinary people who noticed something unusual and acted on it. But it's not just about spotting meteorites. Citizen scientists are also helping to analyze cosmic dust, tiny particles from comets and asteroids that rain down on Earth. Projects like NASA's Stardust at Home invite volunteers to examine microscopic images of aerogel, a material designed to capture dust particles from space. Using an online interface, participants scan for telltale tracks left by Stardust, a task that requires patience and attention to detail. These efforts have led to the identification of rare interstellar grains, providing insights into the composition of distant star systems. It's a perfect example of how technology and collaboration can turn anyone, anywhere, into a cosmic explorer. The impact of citizen science goes beyond individual discoveries. By involving the public in research, these projects foster a deeper connection to science and the natural world. They demystify the scientific process, showing that discovery isn't confined to labs or academic institutions. It's something anyone can participate in. This inclusivity is especially powerful in inspiring the next generation of scientists. Imagine a child who finds a meteorite or identifies a grain of stardust. That moment of discovery can ignite a lifelong passion for science and exploration. Citizen science also highlights the power of collaboration in tackling complex problems. With thousands of eyes scanning the skies or analyzing data, researchers can cover far more ground than they could alone. This collective effort not only accelerates discoveries but also brings diverse perspectives to the table, enriching the scientific process. It's a reminder that the pursuit of knowledge is strongest when it's a shared endeavor, uniting people across backgrounds and borders. Looking ahead, the role of citizen scientists will only grow as technology makes it easier for the public to contribute to cutting-edge research. From apps that track meteor showers to AI tools that help classify galaxies, the opportunities for involvement are expanding. These advancements are transforming how we explore the universe, making science more accessible and collaborative than ever before. And as we continue to uncover the secrets of cosmic relics, we're reminded that the journey isn't just about finding answers, it's about bringing people together in the shared wonder of discovery. By bridging the gap between professionals and the public, citizen science is reshaping how we approach research and exploration. It's a testament to the power of curiosity, collaboration, and the human spirit's unending desire to understand the cosmos. And as we look to the stars, we're reminded that the universe isn't just a place for scientists, it's a frontier for all of us to explore together. The legacy of cosmic relics is more than just a scientific triumph. It's a testament to humanity's unyielding curiosity and our deep connection to the cosmos. These ancient artifacts, from stardust older than our solar system to meteorites that may have carried the building blocks of life, have not only reshaped our understanding of the universe but also inspired generations to look beyond our world. They are more than fragments of the past, they are bridges to the future, guiding us toward new discoveries and reminding us of the vast, untapped potential of the cosmos. One of the most profound impacts of cosmic relics is how they've transformed our understanding of the universe's origins. Before the discovery of ancient stardust or the analysis of meteorites, much of what we knew about the cosmos was theoretical. These relics provided tangible evidence, grounding abstract ideas in physical reality. For instance, the presence of pre-solar grains in meteorites confirmed that the materials in our solar system were forged in the hearts of long-dead stars. This revelation didn't just fill in gaps in our knowledge, it rewrote the story of how our cosmic neighborhood came to be. But the influence of cosmic relics extends far beyond the realm of science. They've become symbols of exploration, inspiring countless individuals to pursue careers in astronomy, planetary science, and space exploration. Think about the Apollo missions, where astronauts brought back lunar rocks that offered unprecedented insights into the moon's history. These samples didn't just advance science, they captured the imagination of an entire generation, sparking dreams of reaching for the stars. Today, missions like NASA's Perseverance rover and the James Webb Space Telescope continue this legacy, using the lessons learned from cosmic relics to explore new frontiers. The ongoing quest to uncover new cosmic relics is as thrilling as it is essential. every discovery, whether it's an interstellar object passing through our solar system or a galaxy formed just after the Big Bang, adds another piece to the cosmic puzzle. These finds don't just answer old questions, they raise new ones, pushing the boundaries of what we thought was possible. For example, the detection of organic molecules in meteorites has fueled the search for life beyond Earth, while the study of ancient stars has challenged our understanding of galaxy formation. Each relic is a key to unlocking a deeper understanding of the universe, and the journey to find them is far from over. What makes this journey so compelling is the sense of wonder it evokes. Cosmic relics remind us that the universe is a place of endless mystery, filled with stories waiting to be uncovered. They connect us to the past, inspire us in the present, and guide us toward the future. Whether it's a grain of stardust or a piece of Mars, these artifacts are more than just scientific specimens. They're symbols of humanity's enduring quest to explore, understand, and connect with the cosmos. As we reflect on the legacy of cosmic relics, it's clear that their impact goes beyond the data they provide or the theories they validate. They remind us of our shared heritage as cosmic beings, born from the same materials that shaped stars and galaxies. They challenge us to think bigger, to dream of what lies beyond our planet, and to continue pushing the boundaries of our knowledge. The story of cosmic relics is not just a story of the universe, it's a story of us, of our place in the cosmos, and of the endless possibilities that await as we continue to explore the stars. As we reach the end of our journey through the cosmos, it's worth taking a moment to reflect on the incredible story these cosmic relics have told us. From the explosive birth of the universe in the Big Bang to the formation of galaxies, stars, and planets, these ancient artifacts have been our guides, offering a window into the universe's earliest moments and its evolution over billions of years. They've shown us that the cosmos is not just a place of vast emptiness, but a dynamic, interconnected system, shaped by forces both seen and unseen. Each discovery, whether it's a grain of stardust, a meteorite from Mars, or the faint glow of the cosmic microwave background, has added another piece to the puzzle, helping us understand where we came from and how we fit into the grand tapestry of existence. What makes these relics so extraordinary isn't just their age or their scientific value. It's the way they connect us to the universe on a deeply personal level. Every atom in our bodies, every breath we take, and even the ground beneath our feet can be traced back to the hearts of ancient stars and the chaotic aftermath of the Big Bang. We are quite literally made of stardust, a living testament to the universe's ability to create and transform. These cosmic relics remind us that we're not separate from the cosmos, we're part of it, woven into its story in ways we're only beginning to comprehend. But the journey doesn't end here. The universe is vast, filled with mysteries waiting to be uncovered. From the search for dark matter and the origins of life to the exploration of distant galaxies and interstellar objects, there's so much more to learn. Every discovery raises new questions, pushing the boundaries of what we know and inspiring us to dream bigger. Missions like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are poised to reveal even more about the cosmos, bringing us closer to answering some of humanity's oldest and most profound questions. The future of cosmic exploration is bright, and it's a future that belongs to all of us. This is why continued exploration and discovery are so vital. Science isn't just about finding answers, it's about asking better questions, challenging our assumptions, and expanding our understanding of the world. It's about fostering curiosity, inspiring wonder, and reminding us of the beauty and complexity of the universe. By supporting scientific endeavors, whether through education, advocacy, or simply staying informed, we're not just investing in knowledge, we're investing in the future of humanity. Every new discovery, every leap forward, brings us closer to understanding our place in the cosmos and the incredible potential that lies within us. So, as we close this chapter, let's carry forward the sense of awe and inspiration that cosmic relics have ignited in us. Look up at the night sky and remember that the stars above are not just distant points of light, they're part of the same story that brought us into being. Stay curious, keep exploring, and never stop asking questions. The universe is vast and its secrets are waiting to be uncovered. And as we continue to explore, we're reminded that the journey is just as important as the destination. Together, let's keep reaching for the stars, knowing that the cosmos is not just out there, it's within us, a part of who we are and who